the theory of strong interaction, and this lies at the interface of theoretical and experimental physics, computational methods, and the optimal usage of high-performance computing machines. And this is what was our motivation in organizing this workshop together with the colleagues from other departments at ETH and the AI Center, from whom you will hear about soon. So I just wanted to bring your attention that other than this first day, which will focus on the general aspects of high performance computing in different departments here at ETH, and we will have some guests from the industry as well. That in the next 3 days, there is also a rich program discussing the needs of studies of strong interaction of lattice QCT and the interface with simulations on alternative hardware, so not only CPU hardware, so GPUs, and also the applications of machine learning in the field of lattice QCT. So if you're interested, feel free to join us also from Tuesday onwards. And now going back once again to today, once again, big thanks to our partners who helped us organize, especially this first day, who are listed here, and AI Center at ETH Zurich and the Future Computing Laboratory. And I'm going to give word first to Alex, right?
Okay. Good. Thank you very much, Marina. So yeah, I'm very excited to be here. Let's see the presentation. Start. Oh, perfect. Good. Yes, I'm very excited to be here. My name is Alex. I'm leading the ETH AI Center. For us, it's very important if we can bring together communities, especially across different fields, different departments, and so on. So if you're not familiar with the AI Center, we have basically 2 core missions. One is advancing interdisciplinary AI research. The second part is accelerating the path from science into society. We're ETH Central Hub for AI. It's a cross-departmental competence center. Now we have over 110 professors, which makes it one of the largest academic AI centers in the world. And our mission is, how can we basically bring the ever-evolving strong part on AI foundations faster to different application and impact areas. We have a fellowship program, which is quite unique, where we have currently the call open, where each doctor and postdoc fellow gets 2 advisors from different fields, sometimes also completely different departments, and they basically sit at the AI Center. So the physical space that we have is also meant as an area to connect and bring people together across different areas. Some examples from our fellows. We started 2 years ago with the AI Center. So now if you come to the AI Center, there are already 60 people physically at the center. So it's already growing quite a lot. And our fellows spanning different areas. So at the moment, if you go to the AI Center, you meet already people from 10 different ETH departments in a very small area, and we hope that this will grow further. So today is also one of the things that if you find areas between machine learning and physics-informed machine learning or electric engineering, more efficient compute, high-performance computing, this might be also a good way to team up between different chairs and work with new fellows on that topic. We do a little bit more than just research, so just a few impressions. We had last week, we had the AI Plus X Summit with over 2,000 people in Zurich as a physical event. We also do a lot on AI and art, entrepreneurship, public dialogue, and also an innovation sandbox for AI together with the Canton. Just to give you an impression, my ask for today is basically try that you meet at least one new person that you didn't meet before. And if you have any ideas of how we can help bringing together a community, you can also use our space, for instance, for meetups. And we're happy if you have challenges or things that are cross-departmental that we can also sponsor them. Thank you very much.
Hello. So it's also for me a great pleasure for being here today. I would just like to quickly introduce you to the ETH Future Computing Lab, which is a new industry-founded research center at ETH that essentially aims to spearhead the development of computing, so future computing, addressing long-term research in the next 5 to 10 years, engaging with industry partners and focusing mostly on 5 core research areas, from integrated circuits to system security, high-performance computing, computer architecture, and computer vision. And our mission is essentially to really leverage relationships between industry and academia to produce world-class research in a collaborative and cohesive way and considerate of global needs. Now, the question is, why do we want to do it? Essentially because computing is something that we need, that it's always present in our daily lives, but we are facing serious challenges, mostly because we are at the end of Moore's law, that has been the main driver of innovation for the past 40 years. So now we need to find new ways to progress with innovation. We need more creativity, for instance, blurring the boundary between computing and memory, implementing heterogeneous solutions. So there are many challenges that need to be tackled. But at the same time, we also have opportunities, driven, for instance, by Internet of Things, but also by AI. And to tackle these challenges and follow these opportunities, we essentially need 2 key ingredients. One being having a really open research environment, and then having top-tier players in the field. And that's essentially what the EFCL is providing. So that's also why we are here today for this workshop, essentially because we see lots of opportunities for the needs from the society, from the application domain, regarding computing solutions to address old problems, new problems. And that's why I also welcome you and enjoy the workshop also from my side.
Thank you very much, Andreas. Yeah. So we're running a little bit ahead of time, but if our next speaker is ready, we can start. All right. So it is my pleasure to introduce. Sure. It is my pleasure to introduce Professor Luca Benini. Let me try to set you up for the talks. This one?
But it's the PowerPoint.
Let's hope it works.
Full screen.
Should we use slideshow or not?
Yeah, full screen. Yeah,
Roman? All right, so while we are setting this up, let me say a few words about our next speaker. So Professor Benini is chair of Digital Circuits and Systems group at ETH Zurich. And at the same time, he's a full professor at the University of Bologna. In his career, he has had visiting professorship positions at several world-known laboratories such as Stanford, EMAC, EPFL, and he has obtained several impressive recognitions for his work, as you can see here, Advanced ERC grant, as well as more recently ACM IEEE Richard Newton Award. And with that, it's a pleasure to have you here and take it away. Welcome.
Thank you very much. So it's also for me a pleasure to be here. And for a change, I will not talk about GPUs and I will not talk about simulation. So I'll just, but it's going to be, as you will see, the dots will connect during the talk. Okay. So actually the best introduction for what I'm going to talk about was what Andrea said a few seconds ago, that is fundamentally high performance computing and computing in general is in a bit of trouble. The reason why it is in a bit of trouble is that we have power bounds. So HPC is power bound. So today we have reached the maximum amount of power that we can reasonably deliver to an HPC center, around a few tens of megawatts. And but we need to keep delivering performance under a constant power envelope. So if the performance goes up exponentially, as it is expected by the application demands, and we have a constant power budget, it means that we need to do more and more work, exponentially more and more work with the same power, which basically means we need to be exponentially more energy efficient. And the rate at which this performance at constant budget scales over time is around 10x every 4 years. So it means that we needed to improve our performance of our energy efficiency of our computation by a factor of 10 every 4 years. This so far has held up pretty well, but you see what happened this year with the exascale. And the first exascale computer, which actually reached the exascale according to plan with a bit of a delay, as you can see, could not really keep up with the energy efficiency. So you see that the green curve, which fundamentally shows the energy efficiency, is pulling up with respect to the requirement. So there is trouble there. However, this is not the largest trouble that we are facing, because there are other areas of computing that are growing in terms of requirements at much faster rate than high performance computing. Machine learning training is actually scaling in terms of computational requirements at a much faster speed than high performance computing, 10x every 2 years. Fundamentally, if the technology cannot meet the requirement of HPC, it will be very, very hard to meet the requirements of machine learning, even though there are some helps, because this is a highly specialized type of computation. Anyway, so if we look at the technology viewpoint, what is happening is technology scaling is continuing, even though at a slower speed with respect to what was 10 years ago. So we're still moving from generation to generation in scaling down the size of our devices. This plot shows the last 3 generations of scaling, including the 3 nanometer generation. It is the one that is getting in production this year. But what is happening is that while density is generation over generation scaling appropriately, power is decreasing, but not at the same rate as the density is increasing. So this fundamentally means that if you have an ISO area chip and you keep cramming more transistors as Moore's law allows to do it, you will get more and more power on the same area of silicon, roughly 24% more power, 1.24 more power for the same area of silicon generation over generation. This, if you put everything together, this actually leads to the fact that you get an improvement in terms of energy efficiency of 10x every 12 years, which fundamentally is at least 3 times slower than what we need for HPC, and 5 times slower than what we need for AI. There is a new trend in technology, which is chiplets, and chiplets allow to mix and match different blocks in your, let's say, single package design. But really what chiplets buys to you is a bit more flexibility and a bit more economical production of high performance silicon. So it's a good thing for making a cost be okay, but it's not actually helping with this energy crisis. So there is no silver bullet there. So what do we have to do fundamentally is to focus on architecture and on design. So try to find the best and highest efficiency architecture. And that's what the community I'm working with, and in general, the people that work from the software down to the architecture, are trying to compensate for the deficiencies of technology. So what do we do? The key idea that I think you are all familiar, because we are here in a workshop that is called GPUs for something, is to go for an heterogeneous architecture, where you have a host which fundamentally is doing a small part of the work needed for your application, and a very wide and large compute accelerator with a very large number of cores, much larger than what we have on the host, and doing a lot of the needed work. So why do we have this heterogeneous architecture? The reason why we have this heterogeneous architecture is that processors can do two types of useful work. One is the decision type of work, where you have control-dominated flows, where you have a lot of decisions to take and not so much data to process. In this case, you need to be fast, and parallelism is there, but it's not a super abundant parallelism. And for this, the high-performance large cores are okay. But where most of the work is today is in the compute part. And the compute is highly data parallel, lot of processes that you have to work on data concurrently, a lot of number crunching, and very few decisions. So by exploiting this heterogeneity and pushing as much as possible the domain specialization of the compute part, so trying to make sure that we design architectures that are good at number crunching on a very large number of parallel data items, we can achieve a higher efficiency than just trying to push the classical control-oriented type of architectures that we have on the left-hand side of this slide. So we'll focus on the rest of the talk on how to design the most efficient compute fabric, because compute is what we want to do. And simulation as well as AI are compute tasks with a lot of data parallelism. So let's look at the hardware now, and let's look a bit at the crucial issues we have to solve. Fundamentally, you can visualize at a very high level hardware at 3 levels of complexity. The first is the processing element, the elementary building block of your computer architecture. The second is how you group together many computing elements on a chip, and the third is how you scale these groups of computing elements at the full system level beyond the single chip, maybe extending to multiple chiplets, as well as external memory systems. So I will look into this in, increasing the scope of where we are looking at and how these things are connected together to design the most efficient hardware architecture at these 3 levels. At the first level, that is what I'm going to focus now, the main challenge is how you feed the execution units that you have in your elementary building block with data, and how you provide operands for your computing units inside the processor. And in this case, the memory is an interaction between the local memory of your compute element and the processing units of your compute elements. And this memory that is local to the processor is a super fast memory, accessible at a very low latency, and typically private of the processor. You can think about in a GPU the registers of your GPU. Then we have a second level where the processing elements will then need to access some shared memory where the data is, and this we call it level 1 memory, where the most frequently needed data is. And finally, we have the L2 memory, where you get the large data sets, and this is the full footprint of your application. So let's look, and in all these 3 levels, the challenge is how you connect efficiently the memory with the processing elements. So let's go for the first one. The first one is, let me take an example, and this is actually a working example that is a tiny RISC-V control core that we use for the baseline of the data processing inside the processing elements. So here the idea is that you want to minimize the cost of fetching, decoding, and pushing into the execution the instructions. So you want to keep this part of the computation as small as possible, because this is not really the computation, it is the control that is needed to support the computation. So it needs to be simple. And second, it needs to be extensible, in the sense that the extensibility of this block allows us to specialize the processor to different application domains, simulation versus machine learning versus others. So simple, extensible, and very important for what comes next, latency tolerant. What does it mean? It means that the access, this core needs to be able to fetch data from the level 1 memory, and needs to be able to tolerate latency in this data coming in. So in other words, we needed to have a unit that is not blocked when there is some waiting for the memory to respond. So these three characteristics are very fundamental, because we want to keep our core busy all the time and doing useful stuff all the time. So minimize the side cost and maximize the efficiency. So how do we maximize how we achieve these three goals? Okay, so the idea is we specialize the instructions of our processor. This is actually a major trend. You probably have seen that this is happening in GPUs with the tensor units that represent a clear direction of specialization of your instruction set for a specific workload, which is tensor processing, which comes from machine learning. But let's try to take a bit more general viewpoint. What is the key problem that things like tensor units are trying to solve? The problem can be seen here. See this simple code, you will recognize it. This is a dot product, the most elementary linear algebra operators that you can imagine, where you're basically summing two vectors into an accumulation variable. And let's look at how it translates into elementary instruction of a processor. And you see that you have to load from the memory, do the additions of your indices for the next loads, and then do the multiply accumulate operations, and then branch back at the beginning of your loop. Okay, this is very normal, right? I think that it's clear to everybody. However, if you look at this is a big problem, because if you look at what is the useful computation in this loop, is the green one. All the rest is extra instructions that you need to be able to do this computation. That is the only useful thing you care about, the multiply accumulate. Okay, so it basically says that 6/7 units of energy of this processor are wasted in doing something that is not the computation you need. So this is the fundamental issue. It's also called the von Neumann bottleneck. Fundamentally, it means that you have to load a lot of instructions to do something that is what you care about. So this is what we really have to solve at the processing elements, how to kill the von Neumann bottleneck. So can we do better than that? And all the architectures, GPUs and others, are trying to address this problem in some way. So how do we address this problem in the examples of the architecture that we design? The idea is fundamentally, let's try to eliminate for the instruction streams the operations that are not the multiply accumulate. And so we will have an instruction stream that contains only the operation we care about. How can we do that? Well, fundamentally, we leverage the fact that, okay, we want this high utilization. We leverage the fact that our computation is highly predictable. Remember, we are in this data-dominated domain, and the computation is highly predictable. So we know what we have to do for a long time in the future, the whole duration of the array. So fundamentally, we can load into hardware what we call an address generator, the sequence, a state machine that will generate the sequence of addresses in the memory without the need to execute instructions. We call these stream semantic registers. It's fundamentally address generators that provide the data the floating point unit needs directly into the registers of the processor, so that we don't need to preload them with explicit instructions. The operation is the same, but we are not wasting instructions in doing it. So the code comes from, becomes now very simple. We just needed to pre-configure our streaming unit, then trigger the FMA within the loop, and that's done. So all the extra instructions that we needed to execute are fundamentally disappearing from the stream. All the load, all the address manipulation, because everything is done in the address generators and is programmed at the beginning of the loop. So this configuration at the beginning of the loop is amortized over all the loop iterations. Okay? So in addition to that, we need to make sure that this happens in an efficient way, so we can tolerate the memory latency. And this can be done by fundamentally having some hardware block that tracks the load issued into the memory system and tracks the dependencies between the load and the FMAs to make sure that there is every FMA gets the right data. And this can also be done in hardware very simply. The last point is how can we avoid to fetch repetitively from the memory the FMA. This is always the same instruction working on different operands. And with this, we can do very easily with an instruction buffer that is storing into the processor itself the instructions that need to be repeated over and over again. In this way, we probably can completely shut down the memory, the decoder, and everything that is needed to fetch this instruction, and they will be quiet, will not burn any power as we are processing our loop. Okay? So this is how we can do it. How does it compare with the GPU? Well, the GPU has a different way to address this problem. The GPU is fetching the instructions, right? Is fetching the instructions, the loads and the FMA, but is doing the same instructions replicated over many units. So in other words, the cost of loading and doing the FMA, this instruction fetch and decode, is amortized over many parallel compute units. That is called a warp. Okay, so this is another way to do it, but it has some shortcomings. First of all, you still have to fetch and decode all these instructions. And second, in order to be able to do that, your register files and the memory, internal memory of your processor has to be very big. And this is a problem because having a big internal memory means that every time you access a register, it is going to have a large cost. So there is some source of suboptimality in the GPU that can be improved in further generation of hardware. So let's put everything together. Minimize control overhead, simple and shallow pipelines, reduce the von Neumann bottleneck, so amortize all this extra stuff you have to do for the instructions you care about, hide the memory latency, and having a high expressive domain-specific instruction sets that are targeted for your domain so that you don't have to translate the key operations you need in many, many instructions. Now, let's move to the second level of complexity, when we have to put several processors to work together and do parallel work and get the data efficiently from the main memory. Now, this idea of creating a cluster where several processors are concurrently getting the data from a shared memory, it's an idea that is pervasive in the computing industry. The GPUs use this idea. This is the Ampere's streaming processor that you probably are very familiar with, where you have a set of processors that fetch data from a shared memory, which is either the large register file or the shared memory, shared data memory. This is a chip that has a very similar architecture that is used for high performance embedded. It's called the Ramon chips. It's used for communication and in space. Very similar architecture. And what you see on the right-hand side is another chip that is used in IoT space, where you still have an array of processors fetching concurrently the data from a shared main memory. So this is actually a very pervasive architectural pattern for data parallel computing. And the reason why people always come to this pattern to develop their own architecture is that it's very convenient to have a set of workers that work on a piece of shared data. Think about a matrix where every worker will work on a row, on a block of your matrix, and the matrix is shared because all the workers will take some rows and columns of the original matrix and produce some rows and columns of the output product matrix. Okay, so this is actually why people always come up with clusters to do the work. What are the challenges in designing a cluster that is efficient? Fundamentally, there are three challenges. The first is to have an efficient processing elements. We discussed that. The important point is the processing elements needs not to put too much pressure on the instruction memory and needs to be able to tolerate a bit of latency in accessing the shared memory. Then you need to have two things to make this array of processor a good parallel computer: low latency access to the memories and the faster synchronization. So a few words how you obtain this in hardware. Maybe you're not hardware experts, but I'll try to give you the intuition. How do you give many processor access to the shared memory space? The wrong way to do it is to create a memory with many ports. And the reason why it doesn't make sense is the memory with many ports is very large and consume a lot of power. So we don't want that. So how do we emulate a memory with many ports? We emulate it with an interconnect. An interconnect that connects several processors with several single-ported memory banks. As long as the two processors are going to different memory banks, then there is an illusion that these two processors are working concurrently on the memory. Of course, this doesn't reduce to zero the probability of two cores trying to access the same memory bank, but spreads the probability of contention over many, many banks. So this is called a multi-ported, multi-banked memories as opposed to a multi-ported memory. Of course, the design problem is how to design this interconnect that has to work very fast and lead and bring the transactions, the requests from the processors to the memories. Okay, so we needed to design this interconnect at a very low latency. Let's assume that we have done this, and there is a lot of experience in doing that, of course, done also in GPUs that have exactly this type of interconnects. Then you have to worry about fast synchronization and atomics. As long as the processor go in parallel, there is no problem, but sooner or later they will have to synchronize. If not, for a final barrier where they say, I'm done, and everybody will wait for each other until everybody is finished. So how do we do this? We have several ways. We can use atomic instructions, and we can also use hardware to help us with the synchronization. So fast synchronization requires some hardware help. Let me give you an intuition on how hardware can help in making faster synchronization and making it also very energy efficient. So it's actually quite simple to understand. Here we have several PEs you see in the bottom that they are doing some work, okay? So the hardware synchronizer will try to make sure that they will start as fast as possible all together. And when they are done, it will try to restart them for the next work all together. So how is this done? Fundamentally, whenever each processor is finished, it will send a signal saying to the hardware synchronizer, I'm done. The hardware synchronizer will stop the clock of these processors. And when the last one arrives, the hardware synchronizer will send to separate wires concurrently to all the processors a signal to say, wake up and go back to work. Why do we want the processor to sleep? Because if they don't sleep, they are wasting energy and power just asking to the synchronizer, oh, I'm done. Oh, are we still ready to do something else? So this is all wasted power, and putting the processors to sleep as they are waiting is the best way to achieve efficient synchronization, not only in time, but also in power. Now, if you apply these things, what is the idea? If you design this type of units, the idea is that now you can synchronize very small parallel regions, which actually is very good, because the smaller the parallel region you can efficiently synchronize, the better is and easier is to program your workload, because you can have very small parallel regions and very little synchronization overhead, even if the parallel regions are very small. Okay. Last but not least, looking at what comes next, we needed to have a very efficient data mover, because the memory, the L1 memory is small, and then we needed to be able to bring the big data that sits in the level 2 memory to us very fast. So this type of data movers, this type of data motion can be done in different ways. There are fundamentally two ways. One is what GPUs do. When they need some data from outside, they will simply access this data from outside the local memory. They will simply access the data. And if it takes time to access it, they will stop the current executing threads and will send into the execution an next thread. they do latency hiding through multiple threads or multiple words that are executed in a very fast context switching, with a very fast context switching. The other way to do it, which is an alternative, but not completely orthogonal, I mean, it can be used in an orthogonal way, but it's a kind of different way, is double buffering. What is double buffering? You create a block of data, you bring it to the local memory with a copy engine that is specialized in doing the copy. And while the processors are concurrently working on the piece of data that you have brought in, the copy engine will work on bringing in the next piece of data. So this is what we have in this cluster architecture. We have all our parallel processors with the faster synchronization. They have and then we have one dedicated copy engine that you see on the side, and this dedicated copy engine will do this double buffering that I was describing. So once we design everything together, let's look at where the energy goes in this the architecture designed for data parallelism. In this architecture designed for data parallelism, most of the power goes where? L1 memory and FPU, okay? Which fundamentally means that this architecture is highly efficient. Whenever you want to see if an architecture is efficient, you have to look at where the power goes. If the power goes to the FPUs and to the local memory, this means that you're not burning power on something else that is not really the fundamental requirements. So this is the direction to be able to design efficient clusters. Now, let me skip a bit of details, but on silicon design of these clusters, let me try to skip to the third part of the talk, the last part, where we look at how we scale beyond the cluster. Now, so we have seen what are the key ingredients to design an efficient cluster, and let's put in red. The idea is how we scale. We need more cores than a simple cluster. We need as many cores as possible to our data parallel application. So how do we scale up? Okay, this is the last question. The first thing to scale up is we needed to create systems where you can put many, many processors close to each other. And this is an example. This is a chiplet-based systems that we recently designed in my group, which is actually similar to what you could buy from the main vendors. And this is, of course, a research vehicle, not a commercial product. So you see the memories that are in the same package, HBM memories like most GPUs have, and chiplets. Each chiplet is a compute entity that has a memory very close and also a capability to spread the workload across two different chiplets through a die-to-die link that connects two different compute chiplets. So how do we organize the computation at the global scale? So fundamentally, the idea is that we take the clusters and we put many of them close to each other. It's similar to what the GPUs do, many clusters in the chip. We needed to give to these clusters the copy engines required to make sure that each of these clusters gets the data it needs. And of course, this cluster will be grouped into other blocks, larger blocks. We call groups. They are called streaming multiprocessors in GPUs. And then we hierarchical scale up the architecture from groups to large number of groups that become the compute entities in your total chip. And then we needed to give enough bandwidth to the remote memory. In this case, latency is not a problem because we manage the latency through the remote copies with the DMA, but we still need the bandwidth because each one of these groups will need a lot of data in a given time window to be happy and fed. So this is where chiplets come into help, because the chiplets make sure that the memory you need is very close to you, so you can get a lot of bandwidth to this memory at a reasonable amount of cost. And also that if your computation exceeds the capabilities of your single chiplet, you can move a part of the computation to another chiplet to scale up the compute capabilities. Now, One last point is I want to stress is what is the main design challenge in this type of architectures, global architecture? It is the network. Because right now we have on the chip and among the chiplets a sort of a network, micro scale network. Sometimes they're called the networks on chips. Okay. Now, a big challenge here is that we wanted to enable this network to allow traffic between the clusters that do the work and the memories, but also among the clusters. In this way, we can reduce the bandwidth demand to the main memory. In other words, if we can construct our data flow in such a way that clusters can communicate to each other intermediate result of the computation, we can reduce the amount of bandwidth we needed to the external memory and actually be more efficient. So that's a big trend today. GPUs as well as other accelerator architectures are really trying to habilitate this type of direct cluster-to-cluster traffic. Finally, we have the chip-to-chip link. The chip-to-chip link has somehow to become transparent and allow resources on different chips to be shared and communication to be very agile. So we need a very high bandwidth link as small cost as possible. And this is what the die-to-die link technology is targeting. Okay, so if you put all these things together, then you can have a chiplet that can give you several teraops of work, and you can construct your system with a chiplet combination and memory combination that is very flexible to your application. So to finalize, to wrap up, what I wanted to tell you is multi-cluster single die scaling with strong latency tolerance and modularity, network on chip to this cluster-to-cluster flexible communication, and full chiplet architectures. These are the three key ideas. Last but not least, I just want to dwell a couple of minutes on the last question. How big do you want to make a cluster? We have seen how you can scale a system to many, many clusters, but how big you want to make a cluster? The answer of this is as big as I can. Why? Because there is actually very old results from queuing theory in the 60s. It's called the Little's law, and basically it tells you that the larger is your L1 memory, the low latency memory, and the larger is the number of processors that you can put in the cluster, the better you will handle the latency of the global interconnect of the memory, and also be able to scale to much larger bandwidth of data in and data out. So the larger the cluster, the larger its local memory, the larger the number of processors we can put in the cluster, the better for your programmability. Now, the big challenge that I'll stop here because I'm running out of time is how you can design these large clusters. And this is actually a very interesting research challenge that I have no time to deal with. So let me just wrap up and show my last slide. So I tried to describe how we deal with the scaling the architectures in performance and energy efficiency in the perimeter of a slowing down Moore's law. So we really needed to do a lot of work at all the scales: processing elements, cluster, and full system on chip. So I explained basically the key ideas: application-specific processing elements, removal of the von Neumann bottlenecks and latency hiding, low overhead work distribution, so efficient synchronization and large pools of processors, and heterogeneous architectures where we have host and accelerator to be able to do the non-parallel part of your work efficiently, and then kick your accelerator to do the parallel part as fast as possible. So this leads fundamentally to the last vision of this technology, where we will use this chiplet to integrate into 3D many compute engines and memory units, and heterogeneous technology to combine memories and logic into a very tightly packed space with long range connectivities, optical based, also connected for the interfaces on the same package of our chiplets. And this is what is going to come for the next generation of post-exascale computers. Thanks.
Thank you very much, Luca, for this excellent overview. Are there any questions? Yes, please. Just a moment, wait for the microphone so that Zoom people can hear us as well.
Hi. Hello, Professor Panini. As your speech is really great speech, and I want to ask, most of the niche, they are targeting the data parallel and data dense jobs. But right now, there's a lot of jobs that use sparse metrics like sparse deep learning, like graph applications. Do you have any hardware support on this on the future plan of the Snitch cluster? Because you know that the NVIDIA, the A100 GPU, they have support on the sparse tensor kernels. Do you have this plan or in the future on your hardware? Thank you.
Yeah, absolutely. Thanks for this excellent question that I didn't have time to cover. But actually, it's not a plan. It's already done. So I just didn't talk about it because of time constraints. You are perfectly right. Sparsity is a big challenge today. Sparse data structure and accessing sparse data structures is a very big challenge. But let me tell you that there is a hope. And actually, if you look into our recent papers already published on this area, there is quite a lot of hope because the type of sparsity we are talking about is not, let's say, similar to what you have in control code. You have actually sparse data structures where you have indices to the non-zero elements that you can access. And actually, the architecture can be adapted. This concept of streaming addresses in the memory system can be adapted to sparse data structures. And so really, there is hope. And as you can see, also GPUs are adapting in this direction. And so the answer is yes, it's a very important concern. And architecture can deal with it. So it's not something that we cannot deal with.
Just wait with the microphone, please. Sure. Are there any other questions? Please go ahead.
Okay, thank you. So about the sparse, yeah, I noticed that sparse have different sizes, from small sizes to a very big size that your DRAM cannot contain. Do you have any plans like the stream you talked about, the streaming on the sparse? Do you have any plan of the reuse of the data from a small size in your local memory to a large size in your DRAM? Mm-hmm. Reuse concern on this.
Yeah, that's also another very important concern. I think this hardware cannot entirely tackle by itself. Let's say, multiple levels of sparsity and the need to reuse the data at multiple levels of sparsity needs some very strong support from the programming environment. And so we need the data structures that help us, and also advanced programming or advanced data domain-specific type of languages that allow us to tackle this. So in this case, it's really, to tackle this problem, you really need a hardware-software cooperation. Architecture by itself cannot solve this problem alone. But also this, I think there is some very interesting work being done, for example, by Professor Thorsten Hoffler in the computer science department that is exactly in this direction. Domain-specific languages to handle sparsity in data structures and handle it efficiently together with efficient hardware for doing it.
Okay, thank you.
So thank you for mentioning that. I think we will hear a little bit more about the work in Professor Hoffler's lab. So let's use this chance to thank Professor Benini again. Thank you. All right. Can somebody help us set up for the next speaker? Still have a few minutes. Yes. All right. So our next speaker comes from our industry guests. So this is Bill McCall, who is director of Huawei Research Center in Zurich, and in particular their Computing Systems Lab. Bill is also a fellow of Wadham College at Oxford University. And before taking this post at Huawei in Zurich, he was a professor of computer science, head of research in parallel computing, and also chair of the Faculty of Computer Science at Oxford. So Bill's current research focuses on new foundations on supercloud computing, and I assume he will tell us a little bit about that in his talk on future architectures for computing and AI. Bill, welcome, and please take it away. So this is microphone, but if you would prefer to move around.
This is fine. Well, first of all, excuse me. Thank you for inviting me. It's great to have the opportunity to attend this event. I'll do two things. First of all, since I expect most of you will know very little about Huawei, in particular Huawei in Zurich, I'll give you an overview of who we are and what we do. And then I'll talk about some areas that I've been working on for new models and architectures for large scale, essentially cloud computing, but moving beyond the kind of cloud computing that we have today. So let me sort of go top down. I'll say a little bit about Huawei and research, and then I'll talk about Europe and then about Zurich. So this is a chart from the EU from last year, in which it lists the top companies in the world in terms of their R&D expenditure. And you see number one is Google, Alphabet, and Huawei is number two, ahead of Microsoft, Samsung, Apple, Facebook, Intel, and other companies. So we are a major global company in terms of investing in R&D. Also, since you may know a little bit about Huawei, it's probably useful to say that we're essentially a full stack technology company driven by this kind of research and innovation that we fund. So we basically do pretty much everything. We produce CPUs, GPUs, AI accelerators. We produce clusters of AI accelerators. We're the global leader in communications technologies. At the moment, 5G, moving to 5.5G, and doing initial research towards 6G, and also optical technologies, which Luca just mentioned a moment ago. We have a major business in servers, also in storage. We are one of the, let's say, top 10, although not yet top 3 cloud companies in the world. We produce mobile devices, automotive computing technologies, and we also produce a lot of open source, major open source software systems, operating systems, databases, and AI platforms. So in some ways, it's kind of easier to say what we don't do. So we're not a content company. We don't compete directly with Google or Meta, say, in the area of social media or content and search. We're basically a technology company producing pretty much every area of technology that is around today, both hardware and software. So as I say, we have been producing CPUs. Mostly our major high volume CPU products are ARM-based at the moment. We also produce GPUs, and we have a whole family of AI accelerators, from very small ones for edge devices, simple edge devices, all the way through to training chips. We put these into clusters, such as shown here. And as I say, we produce open source software, operating systems, operating systems for both servers, and that should have actually been mobile. I was too busy writing cloud. So for servers and for mobile devices. Oh, it's below here. Okay. So basically, we produce operating systems for servers and cloud. We also produce operating systems for devices, phones, databases, and AI platform. As I say, we are a growing cloud services vendor as well. We have pretty much all of the same types of services offered by the three major US cloud vendors. And just a few days ago, we announced that for the first time, we're bringing cloud services to Europe for customers in Europe. So that's just an overview of the company. It's a very big company, as you can probably tell from what I just described. It's about 200,000 people. But we also do a lot of research, and we do a lot of research in Europe. So we have about 25 different research centers spread all over Europe. Some of them, well, most of them focus on different areas. For example, in Stockholm, we do a lot of communications. In Paris, we do communications. The one at the bottom, Zurich, is one of the newest, and its focus is on computing. I'll say a little bit more about that. So within these European research centers, we basically fund, in addition to doing internal research in an open way, we also fund academics, professors, postdocs, students all around Europe in open research projects. We give prominent professors gift funding of various kinds. We build joint labs as well as doing our own research. In Zurich, 2.5 years ago, we launched a new computing systems lab here in Zurich. And this is set up to become the major center in Europe for the long-term research on computing systems that Huawei is doing. So basically, we're doing open research. Everything we do is open. There's no proprietary product-related R&D that is commercially confidential done in this lab and in the others. So we're focusing on fundamental theory, software, and architectures for future computing systems. And we recognize that we can only do part of that ourselves, that we need to partner with leading researchers and academics in Europe to address some of the grand challenges that our industry faces, and together we can try to solve. That will be good for our industry, and if it's good for our industry, that will probably be good for us as well. But we're not looking to solve problems exclusively for the benefit of Huawei. And in the lab already, after 2.5 years, we are focused on a whole wide range of areas. So again, we're kind of like a full stack research center. We do work all the way from CPU architecture, accelerators, memory systems, storage architectures, hardware, software, co-design, pretty much everything you would expect through areas like new compiler technologies, MLIR, and of course, parallel computing and HPC. So this lab will keep growing very significantly and keep expanding both the breadth and the depth of what it does. Okay, so that's just a kind of brief introduction to Huawei and Huawei in Europe and Huawei in Zurich. So the second part of the talk, I just want to give a personal perspective on not every aspect of future architectures for computing and AI, but a personal perspective on some aspects of what I expect to happen in this area. So if we look at computing today, there are some already existing clear dominant trends. An obvious one, open source software, which I've mentioned a number of times. That's now been dominant for many years. There's no likelihood that that's ever going to go away now. So open source software is here to stay. Obviously, this now extends to hardware as well. Lucas has been talking about RISC-V related systems and open hardware and so on, open ISAs. These are all unstoppable trends that will just become more and more important. So open source is perhaps the biggest single trend that's shaping our industry in a very significant way. In my view, the other one is cloud. So cloud has now been around maybe 15, 17 years or so since Amazon started. And all throughout that time, people have said, well, maybe cloud will grow for a few years and then it will decline again and everybody will go back to having their own in-house systems and so on. And there are some companies that have gone to cloud and then returned to in-house systems. But it's a tiny, tiny percentage of companies that have done that. All of the momentum in large-scale computing today is towards very large-scale, so-called hyperscale data centers and cloud infrastructure. And you can see it in the way money is spent today in computing technology, IT spending. Depending on which numbers you believe, but certainly probably more than 50% of all expenditure on technology today is by a very small number of companies, so-called hyperscalers or cloud companies. And they're not just buying from technology companies. In almost all cases, their businesses are at such a scale that they're already designing their own hardware. They don't want to wait for Intel or any other company to give them what they want. They're moving beyond that to designing their own chips and architectures. So cloud, in my personal opinion, is definitely here to stay, and it will just keep growing and growing to the point where pretty much all large-scale computing will eventually be handled by these sort of hyperscale cloud centers. But if you look today, actually what's done in cloud is still pretty limited. We've had 17 years of renting servers and renting storage and serverless and so on. By and large, it's still business and web apps that are using cloud. The national labs that do HPC in this conference, this workshop is about things like QCD, physics, physical simulation. The labs that do that by and large don't yet rent from Amazon or rent from Google. But my strong expectation is that they will. They'll use the cloud as well. And that's what I want to talk about. What do we need to do in order to get to a point where pretty much cloud is used for everything? And that'll be the theme of what I want to talk about. A couple of other trends that are going on at the moment. Another one is disaggregation. It's hard to say how quickly this will unfold, but certainly related to cloud, but not exclusively to cloud. The inflexibility of large-scale system architectures is perceived as a major problem that we have because of the way we build large-scale systems. We can sometimes get a lot of resources which are inflexibly organized so that we're not able to take full advantage of them. For good historical reasons, we've always kept compute and memory close together, or kept compute and storage close together. But it's a trade-off. It's a trade-off between immediate performance advantage and large-scale flexibility. And people are certainly experimenting with new types of architectures which are increasingly disaggregated, where you just have pools of compute, pools of storage and probably pools of memory as well. So that's another trend that will play out. And then even in hardware, we're sort of still in the mainstream of this phase where everything is discrete, separate devices. So we have the CPU market, we have the GPU market, we have, for some companies, big and small, producing AI accelerators. But again, another trend that you can see already in the latest, if you look inside the Apple chip, for example, everything is kind of converging again in lots of areas. People want to have devices that have more than just one capability. So this is certainly, the dust is not settled on this, but it is another trend that probably will happen. So, so let me talk specifically about this cloud area. So cloud, as I've said, is mostly today business and web apps and just renting servers or renting storage. But my view is that everything will, pretty much everything, not IoT in the edge, but all large scale, pretty much all large scale computing will eventually become cloud services. But my argument is that we're far away from being able to achieve that. But I do confidently expect that by, say, 2030, pretty much all HPC, all AI, large-scale AI, physical simulation, which is related to this particular workshop, and is indeed a rapidly growing area, data analytics, large-scale knowledge bases, that all of these will basically become commercial cloud services. And there's no shortage of applications that will drive this kind of transition. And not only will each of these individually move much more to the cloud, the really exciting game over the next 8 or 10 years will be to build completely new applications and services that combine HPC and AI and physical simulation and analytics and knowledge to do things that we just cannot do today at all. So a lot of the big challenges long term will need improvements in all of these areas, and we'll need to be able to do them together. So my hypothesis is that that's where we want to get to, but we're very, very far away from that at the moment. If you look in most systems, I wouldn't say all systems, but I'd say most systems that are used today for HPC or physical simulation, or indeed AI training for that matter, they're not really designed to be used in anything like cloud services mode. So actually, they're very good if all you want to do is run a single application on a single dedicated machine and everything works perfectly. There's never a fault. There's never a long tail. But the reality is that that's the tip of the iceberg. The rest of it is what we need to actually figure out in order to make the kind of scenario I described real. So what are the research challenges? Well, it's a very long list. So first of all, instead of running one application or maybe 2 or 3 applications, we're going to need to be able to run hundreds, possibly even thousands of applications and services simultaneously. All kinds of data will be coming in continuously, and everything will need to be updated constantly. Probably we'll have disaggregated hardware. And to run any commercial cloud service, you need to be able to have guaranteed quality of service, even when priorities are constantly changing, deadlines are emerging. You need to be able to handle fault tolerance and tail tolerance. And you need to be able to optimize the whole architecture continuously to make sure that you're operating as effectively as you possibly can. And I'll come back towards the end to talk a little bit about data because it's an interesting, challenging area. So basically, there's just so many problems that we do not have a solution to today that will basically block us from moving to the kind of scenario I've been describing. So I won't go into this in detail because I don't have time, but basically one thing I'm doing at the moment is coming up with a model for essentially being able to do what I just described. And it's, rather than go into details, is what I would say is we're trying to build compute for intelligence broadly. And what we actually need to do is also to build intelligence into the compute in order to be able to handle all of the challenges that I just described. So let me just talk about a couple, 2 or 3 of the problems. So first one, I've worked in HPC for more than 25 years. I ran the HPC Center at Oxford for about 10 years. Today's HPC is pretty much the same as it was 25 years ago. Hasn't really changed that much. Yeah, we have GPUs today. We only had CPUs back then. But by and large, the way systems are built today for HPC is exactly the same as we had in the 90s. And sadly, a consequence of that is we still have the same problems we had in the 90s, and they've never been solved. So one is, here's a headline from a couple of weeks ago, that the new machine at Oak Ridge, basically they can't get it going for any length of time. There's problems arising here, there, and everywhere. So this is a scenario we spend tens of millions of dollars, in some cases like Fugaku, hundreds of millions of dollars, to build a supercomputer which can probably only do a small number of applications at any one time, maybe one, certainly a small number, and it's just not a basis for any kind of commercial business. Now, of course, if you're a government lab, you're not operating a commercial business, so you can get away with it. But there's no way that Google Cloud or Microsoft Azure or Amazon or Huawei or Alibaba, any major cloud vendor, could operate HPC as a service on something like this. Just it's a non-starter. So this is a problem handling faults and tails, and unfortunately, it's not just faults. So this is about faults. But actually, faults are the easy problem. The hard problem is tail latency. That as soon as you have large-scale systems with complex, modern, bloated software, you get all kinds of tail latency for all kinds of reasons cropping up. So Google have recognized this for the last 15 years or so, that basically you can run simultaneously 1,000 different processes, and they should all take 1 second. But when you look at how long they've taken, it kind of looks like this. You know, most of them take roughly the time expected, but there's a very long tail of responses that you need to be able to handle. So again, I don't have time to go in, but this is a problem which can be solved. Scheduling. So even scheduling in traditional parallel computing is a non-trivial problem. How to map a parallel computation onto a given number of nodes with set, making sure that the load is balanced, the communications minimized, the amount of synchronization you need to do is minimized, local memory is organized in the right way, etc. But pretty much we do know how to do that. But in these new systems, we're going to have to do much more than that. We're going to have to co-schedule large numbers of computations which will run concurrently. And even at a trivial level, this is a non-trivial problem. So suppose we just want to do something like this. I've got 4 task graphs here, and all I want to do is just to run all 4 of them. But they're 4 separate computations, very simplistic example. Well, obviously, if we want to run them as fast as possible, we just take as many resources as we can get. So if we take 12 nodes, we can run them like this, and that'll be as fast as possible, probably as expensive as possible as well. Or we could run them sequentially, basically. That would be very cheap, but it would take much longer. Or we can schedule them this way, which is kind of cheaper, but not too bad in terms of performance. But again, this is just the tip of the iceberg. The scheduling and co-scheduling problems are extremely complex. We're trying to balance load, so balance the computational load, of course. We're also trying to balance the communication at all points in the system to make sure that there aren't bottlenecks in certain areas. We're trying to make sure that we minimize local memory requirements across the system as well. We need to be able to schedule so that we optimize for differing priorities. Maybe some of the applications are high priority and other ones are low priority. Maybe some of them are deadlines, etc. And this is sufficiently complex that there's no one solution that deals with all of this. You have to deal with trade-offs. There'll be trade-offs between some of these. So again, this is something which is basically, I would argue, a solved problem, and that we do know how to do this, although it is complex. So last topic is shared data. So again, one of the things about, since it's a workshop about scientific computations, physics computations, and so on. So one key characteristics, this is the second last slide. One of the key characteristics of the growing number of scientific range of scientific computations that take place, just enormous amounts of data. And of course, we've had 40 years to look at how to deal with data, starting with, of course, relational databases, moving on to the whole big data era when everyone started to get interested in relaxed consistency, key value stores, more recently with machine learning, parameter servers, and of course, in the background, growing large-scale knowledge bases. So large amounts of data are going to be essential to all of the things I talked about. So what do we know about how to handle data efficiently in large-scale parallel systems? Well, one thing we know is that shared memory doesn't scale. We've known that for 40 years. So just saying, well, we'll put it all in shared memory and that'll solve the problem, that's not a solution. Okay, what else do we know? So we know that if we really understand which parts of the computation need which parts of the data, then we can, in simple cases, we can shard the data in lots of different ways to handle that situation. We also know that if the data is only read-only data, then there's lots of things you can do as well. You can partition it, you can replicate it, as long as it's read-only. The core problem in large data that is a solvable problem is basically where you have random or so-called non-oblivious access to the data. That is, you can't predict statically what the accesses are going to be. So the data, think of it as random access to a very large data set. But it's also a data set that's being updated frequently, and therefore it's not static. You cannot deal with it once and for all at the outset. You have to continuously update the data. So that's the challenging problem. And usually, historically, what people have said is, well, if I face all of that difficulty, I'll just try and use some kind of shared memory. But of course, that doesn't work. So one new development, which I've been working on, there's also some work at Stanford on this on very similar lines, is basically to say, well, is there anything that can give in all of this? So if your objective is to do online transaction processing and you need ACID semantics, there's nothing you can do. If you need that, You cannot do that at very large scale, in very large scale parallel systems. But that's usually not what people need to do. They're not running banking transactions. What they're running are petabyte or exabyte scale data sets being operated on for scientific computing, machine learning, etc. And the key to finding a solution, a new solution to get out of this very important practical problem is to recognize that not all of the processes will be accessing all of the data at the same time. And that's just a question of scale. So this again, we now know how to do this, and it's actually a very important practical problem that can now be solved. And there's just I won't go into details of this, but essentially, what you want to be able to do is to have a centralized picture of where this shared data is, and make sure that when updates happen, a little bit like just providing invalidation notices to the node, you can actually do this. So that's all I had to say. Thank you again for inviting me, and happy to answer any questions if there are any.
Thank you very much. Are there any questions for Bill? So I forgot to mention for our participants on Zoom, feel free also to ask questions. We will monitor the Zoom chat in case you want to ask something. I don't see any questions in the room currently. Let me maybe ask one. So you were saying that for machine learning applications, we would need dedicated architectures. Do you have any example of scientific applications of Huawei's architecture being used for high performance computing?
Specialized ones.
Specialized ones, yes.
Yeah, of course. So David Shaw in New York has been building this Anton system for molecular modeling for about 10 or 12 years now. And people have certainly talked about QCD machines, and so I remember that from like 25 years ago. People were talking about that. As we all know, the problem in our industry is that as soon as you say you're going to design something specialized hardware, in the glory days of Moore's law, the general purpose devices kept basically crushing any progress that you would make on specialist devices. But certainly in the last, the exception is GPUs, of course. So GPUs with graphics, and then more general classes of computation, and of course riding the wave of AI. So they've clearly been successful. There's no doubt about that. Whether people today, many people want to build specialized hardware beyond what we already have. There is actually an area, but it's not what you're asking about. The whole area of infrastructure processing is an area where people are designing chips now, so-called DPUs, recognizing that in large data centers and in cloud, a lot of the time your CPU is taken up handling infrastructure stuff when it should be doing compute.
Locally, yes.
Like in Luca's talk, he separated out the control issues from the compute issues. So this is, of course, it's a major problem. So people are doing that, but in terms of, say, QCD or something, you probably, you wouldn't do it probably as a commercial product, but I don't know how big the market is. I do know the market for physical simulation is going to be much bigger than it's ever been. So very broadly, if you take something between HPC and physical simulation, all of this desire to build digital twins of everything so that we can understand a complex physical system through its digital twin. That will drive a lot of innovation in physical simulation. There'll probably be other things as well. So I'm actually very enthusiastic about physical simulation as a big growth area for the future. So it may well be that some of the things that we do there will be sufficiently high volume that you could justify building a specialist device. But obviously people like, as I say, David Shaw's group in New York that did Anton, they did it sort of before, they started to do it before the GPU revolution happened about 10 or 12 years ago, and when and the whole AI thing. So I'm not sure that it really is that much better than you could do with something you just buy from NVIDIA or Huawei or anyone else.
But still on a dedicated computer center. So
but yeah,
doing that on the cloud.
I mean, I think the key thing will be, is there an application area that is sufficiently big that the effort is justified? I'm talking commercially.
Sure.
Of course, the reality is Luca's group here at ETH, they build chips continuously. So it's no longer as daunting as his group and others have shown. It's no longer as daunting to build a chip for some particular purpose as it was, say, 20, 25 years ago. The costs are much lower. RISC-V has obviously opened up a lot of new opportunities. So yeah, I think people will build specialist devices, and some of the areas will become sufficiently big and important commercially that they'll even be commercial devices. Yeah.
Excellent. I think you gave us some great ideas. Any more questions for Bill? Yes, please, in the back, Bartosz. Just wait for the microphone, please. Go ahead.
Hi, thanks for the talk. I wanted to ask, you mentioned that you see in your vision HPC moving to the cloud. Now, as a practitioner, we already have trouble moving data between HPC centers, which are exceptionally well connected between each other.
Yeah.
How do you see this happening in the cloud? What about the energy costs of moving petabytes of data, hundreds of kilometers, thousands of kilometers?
Yeah, it's a very good question, and of course, those who have actually talked to cloud vendors about putting more of their workload onto cloud. Of course, as most of you probably know, the cloud vendors are very smart in that they will allow you to put your data in easily, but getting it back out again is usually much more costly. So yeah, moving. We all know the anecdotal stories that the cheapest way to move an enormous amount of data is by Federal Express. Just put it on physical devices, put them in a nice cardboard box, send them to Pasadena and unpack them again. That's the quickest way to do it. That was the case 20 years ago. And I think it's probably still the sizes have grown, but it's still probably the best way. So it is a good question. I think though that the cloud vendors will try to make it, they will probably take the cost hit by getting that data from you if you allow them to do it. I mean, the alternative is you just keep it to yourself, and then you've got to manage everything. And they will come to you with a proposal that says, we'll take all of that worry and care off your hands, and we'll make it attractive to you. Because once they have you, then this kind of the inertia of the data will make sure that it doesn't move too far. So I think there's sound business reasons for cloud vendors to want to get HPC, and any commercial vendor, they're all the same. Everybody will find ways to attract you to buy into that. You know, if you're a government lab and you've got a 20, 30-year perspective, and you know the government is just going to keep funding your lab, you don't need to do it, of course. But a lot of people, my point is that HPC will no longer be a niche of government labs. It'll be a mainstream activity for a lot of the things that people want to build. You know, digital twins, smart healthcare, you know, all of these things will involve simulation and modeling and so on. So it's a good question. I think there are commercial solutions to it, but there's no doubt that for a whole variety of reasons, some government labs will not, government-funded labs will not do that. But that's okay. I think the key thing is that the people who want to do HPC applications in order to build a whole range of new intelligent applications in the future, they probably will do it because they don't want to have an army of people writing MPI code directly and managing the system.
All right.
Okay.
Let's thank Bill again.
Thank you.
Thank you very much. There was a question. Oh, sorry. We have one more question via Zoom. I didn't see it. Could you please? So let me try to unmute. Can you do it there, Roman, or should we do it here?
I think I unmuted.
Yes, please go ahead, Steve.
So last time I checked, it seemed very cost ineffective to get HPC services on the cloud. I'm wondering if Huawei offers HPC nodes with, say, GPUs, perhaps something similar to Perlmutter with 4 A100 GPUs, and how much would it cost to rent such a node for an entire year?
Yeah, so yeah, normally when I give talks, one thing I try to avoid is ever commenting on any other companies' products or offerings or doing comparisons. But certainly we are, compared to Amazon, Microsoft, and Google, take the 3 main US cloud vendors. In China, it's Alibaba is the main cloud vendor at the moment, and we are the number 2. So we have come to this area a little bit later than others, but we do have all of these devices, and we have new devices that we're developing in broadly the domains that you talked about. And we definitely do think this is a major growth market in the future. But I can't today give you a price for what that would cost over a year. But clearly, if it's not competitive, that market will not grow. So I think the cloud vendors will be highly competitive in trying to win this business. I don't think there's any doubt about that. But I couldn't give you a number for a year's worth of HPC-oriented cloud capability.
All right, maybe we can try to understand this offline, but if I understand correctly, the service exists, but the price is not.
Yeah, the services do exist, and we certainly want to do a lot more. Our cloud services are like Amazon, Google, Microsoft. They're mainstream cloud services at this point. As I indicated, we just announced that we're coming to Europe for the first time. And certainly as a company, we think that these areas of high performance systems are the next obvious major growth area for cloud.
All right, thank you. So the question was asked by Steve Gottlieb from University of Indiana, our colleague from the US, so he might be able to access it already. Thank you very much, Bill, once again. And we're right on time for our next speaker. So just a quick announcement. So we will have 2 more talks and then the coffee break, followed by some student talks and the panel discussion. So Our next speaker is Tal Ben-Nun. I'm having trouble finding your slides here. You're sharing the screen. All right, excellent. Even better. All right, so Tal is a member of Scalable Parallel Computing Laboratory led by Professor Thorsten Hofler, mentioned several times today. So before joining SPC Lab, Tal was previously a member of Distributed Computing and Scattering Labs, as well as Parallel Systems Labs at Hebrew University of Jerusalem. And in today's talk, he's going to tell us a bit more about scaling machine learning and scientific computing from a data-centric perspective. Take it away, Tal.
Yes, thank you. Just trying to see if this works. Okay, that's a bit of a delay, but we'll manage. So yes, exactly as you said. So I am part of SPCL, the Scalable Parallel Computing Laboratory, led by Professor Thorsten Höfler. And there I've been working with an incredible group of people for, I guess, over 5 years now on this amazing project, where essentially what we're trying to do is, we're trying to ask ourselves, how can we rethink programming, like based on all the things that we've heard today, mostly related to data, right? We heard data centers, we heard about data movement on the hardware level. And what we're trying to understand is, can we support the process of performance optimization and performance engineering, and can we even take advantage of all the low-level performance benefits by using high-level languages, right? So this whole thing is going to be interesting. Okay, good, perfect. So I'd like to start with some example that, I don't know, I guess most of you are quite well intimately acquainted with. So let's say you have your computational problem, and I don't know, let's say you're solving some numerical integrator that is supposed to predict the weather. And let's put a twist on this problem, because these days, really, it's very common to try to use the best and latest hardware. And for that, one of the applications that uses the hardware the most efficiently is machine learning. So you want to try running a neural network to try to solve that. So you open Google and you try to find some system, and there is a classifier that you can find online, which is basically a system that can distinguish between, I don't know, cats and dogs or something like that, right? So you say, okay, great, let's try to put my system onto that and, try to take this problem, and suddenly it's not so plug and play as you were led to believe, right? So why? Many reasons. But first and foremost, the world or the things we're simulating are not 256 by 256 pixel images, right? They're much bigger. And I'm going to give a concrete example in just a bit. But on top of that, if we really want to go further, then this thing gets much worse when you're trying to use the current, I don't know, leadership computing facilities. You want to use the Fugaku supercomputer that uses an ARM CPU. Okay, no longer do all the systems, that work with NVIDIA GPUs nicely, and AMD GPUs even. That's the future, right? The Frontier supercomputer that was just mentioned, and even other future architectures that we can't even think of right now, right? So at this point, you're kind of at a loss, right? There's nothing you can do to go and optimize that. Everything is all built from pre-computed, pieces, and what you would need to do is, I don't know, hire a performance engineer or a team of performance engineers, right? But more often than not, we're dealing with research here. We're not companies. Have to undertake this role yourself, right? And that, again, is quite challenging, and it gets more and more challenging the further we go into this Cambrian explosion of architectures that we have, right? So this is happening, and I can tell you from personal experience in X-ray diffraction, as just mentioned. This is happening in astrophysics. This is happening in computational medicine. This is happening everywhere, where we really have this problem of performance engineering, and now we have this machine learning on top that is also very, very challenging. So just to give you, again, this concrete example, let's talk again about weather prediction. So there is a data set called ENS10, okay, Ensemble Weather Prediction Systems. This is a 20-year data set that we need to train and see maybe we can use machine learning to improve the accuracy of weather prediction in general. The tensors we're getting as an input here, they're quite big. They're 5-dimensional. They have 720 by 361 latitudinal longitudes grids, 7 parameters, and 11 pressure levels, which are height points, and 10 different ensemble members. Already you can see how this doesn't really fit, right? And more than that, I can tell you that it's very hard to fit that on a single GPU properly, right? So you can, shard your data set as much as you want, but a single sample, if a single or two samples don't even fit in a single GPU, then you're going to have to go into distributed computing just to train something very simple. So it takes several days to train. But the positive fact here is that if you do this performance engineering, you can actually get quite an interesting improvement, like 11% accuracy improvement in extreme weather events, right? So this is really important, right? So we want to get there. So at kind of the center of scientific computing, machine learning, and performance engineering, this is, again, my kind of personal goal here, lies data movement. So the key that I believe would be the most useful to optimize applications, and I'll prove to you that in a bit. And of course, I mean, this has been proven by Professor Bernini just before, is that we need to optimize and minimize data movement right now. Right. So what the hardware claim here is that for the past more than a decade already, according to the plots that we've just seen, it's way more energy efficient to multiply two operands than to actually bring those two operands onto the chip itself. Problem, of course, gets worse as we get to clusters. Energy costs are quite quite high, and the thing is, this also comes into play into the software itself and the software APIs. So this is an NVIDIA code sample, the simplest code sample for matrix multiplication with tensor cores. Okay, this was taken directly from the SDK. 333 lines of code. 332 of them are for moving the data into the units that multiply the two matrices. Right? There's one line here that does the MMA. So that's what we're at. Most of the optimizations that you'll do on CPUs, GPUs, FPGAs would be in data movement minimization. Vectorization can be considered a form of data movement, because you move the data into the vector registers. Can really kind of take a lot of things that you would normally apply, and you can put that under this umbrella of data movement minimization. And so the question is, okay, we know this. We've known this for a while. That optimizations, we have to write them. But now we have machine learning, and that's super promising. And this kind of, alleviates the problem. We have so many different things that we can do, right? The state of the practice, like we have DNN compilers, deep neural network compilers that promise really a lot of performance, right? So we have XLA and JAX and then TVM and then Triton, and they really kind of, have this idea of you get your neural network in, this is built of simple building blocks and simple components. We're going to optimize this for you. But the actual truth of the matter is that the view in which they optimize the applications is very operator-centric. By operator, I mean like a convolution or a matrix multiplication. So if you see something like that, it immediately gets translated to a library call, if possible, right? Which leads to kind of interesting effects, right? So I just measured here convolutions, 1, 2, 3-dimensional. And we can see, of course, 1-dimensional convolution performs kind of less efficiently than 2-dimensional, but also 2-dimensional convolution performs less efficiently than 3-dimensional convolution by a margin. And that is kind of a bad sign for someone who's doing scientific computing, where 3-dimensional convolutions are quite common, like in astrophysics, for example, and so on. And if you want to take that problem even further, even in the 2D regime, what we see is that if we have convolutions with non-standard sizes, we can see some odd performance characteristics, right? So ResNet 50, that's arguably the most popular convolutional neural network to this day. And so there, most of the neural network compilers and frameworks, they do reasonably well. But then wide ResNet 2, that's the same as wide ResNet, but just multiplying the channels by a factor of 2. Okay, so essentially, theoretically, number of floating point operations, number of data, like movement and everything, just a factor of 2. But as we can see, performance, it actually doesn't behave 2 times slower, right? It's actually closer to 3 times slower depending on the compiler, which kind of leads you to think that there may be places to improve on this whole idea of deep neural network computation. And if we go back to distributed, then most of the distributed libraries, what they would give you is a very specific form of data distribution that is more about the data set itself rather than, I would say, like the model like we wanted, or the parameters or other very scientific computing specific schemes, right? So we're left with this basically to solve on our own, right? And if we don't have the tools to do that, if we don't have the performance engine or the capability, we cannot distribute, we cannot train, we cannot get to the results that we would want, right? So what if we take all of this and say, I want to turn it into a programming model, or more than a programming workflow. Okay, and that's the Data-Centric Parallel Programming Project, or DACE for short. And that's a certain, like a framework and a workflow. And basically it starts with the idea that there is a separation, or we acknowledge the existence of a performance engineer. Okay, because even not as a physical person, but as a role, it always exists. It's never that you run a compiler and you compile your program, you build it, you run it, and that's it. It's not like that. You know, the cases change and the models change and optimizations change and then the systems change, right? So in that sense, we just try to acknowledge this by saying you write your programs in a domain scientific way. And I'm not saying high level languages on purpose here, because we have high level languages like Python, but also C, right? Or domain specific languages like GT4Py or, you know, PyTorch for neural networks. And I'll get to that. Then what we do is we undergo a certain process of conversion into another kind of representation, an intermediate representation. So not unlike what compilers use, but a bit different here, because here what we focus here on is data movement and data movement minimization. And then we undergo a few transformations on that representation without touching the original code, right? So in that sense, you can write your files, you can write your deltas on this file that is completely separate from the code. You can even update your code to some extent, and none of that, like none of the optimizations would be changed or modified. So unless you change the data flow of the application, some of those optimizations can still be applied. Then we map it onto a wide variety of hardware architectures, CPUs, GPUs, FPGAs, clusters thereof. And that's not the end of the story, right? That's where actually the story begins. You get back performance results, you get back instrumentation, you can go and you can keep optimizing that further and further until you're happy with the results. So that's the idea, like this white box approach, kind of open view of optimization, very supportive of the ones who are actually doing the optimization, but also the ones who are writing the programs. So just to maybe briefly say what this representation is all about. So I'm not going to get into the details, but it's a fundamentally different way to think of programs, right? So the way that compilers have evolved and a lot of things, a lot of compute has evolved is basically to go through instructions as fast as possible or as few instructions as possible, right? And compilers were doing that first. Then they added data flow to augment this computation in order to optimize a few things. Here we're trying to go exactly the other way around. We start from data flow and we introduce control flow as we have to. So control flow means if conditions like branches, loops, anything that cannot be implied with data flow. So the first step is to say data containers, arrays, queues, whatever you want to use, they're separate from computation. So in our representation, they are, you know, the data containers are kind of oval nodes here, and the computations are what we call tasklets. These are kind of octagonal nodes, and they cannot do anything on the memory that is not given to them by edges in and out, right? So that we kind of force onto the system so that we can do a lot of optimizations. Now, the next step is to introduce coarsening or different granularities. So in the control-centric world, let's say you would have function calls and classes and modules, right? And those are things that govern control flow. You jump into a function, you jump out of a function. Here, it's more, what is the granularity of, let's say, am I operating on a scalar? Am I feeding in a column of a matrix? Am I feeding in a whole tensor and so on? So we can really express those basically with scopes. Like this is a parallel scope, which we call a map, which can just do a symbolic number of parallel computations. And we have also a concept called library nodes, which is basically, we know the semantics of this node. Maybe we can do some interesting transformations. Like if a matrix multiplication is flowing into a transposition, let's remove that. But that's not the focus. The focus is really to operate on this data flow. And yeah, so then basically all of our computations, all the program order, everything derives from the data movement first. And only if we can't, we introduce control dependencies. So basically this whole computation, I mean, it's very hard to see on the screen, but there is a rectangular cyan rectangle here, and that forms a state machine. So then if you have a data oblivious application, you will be able to very easily see that. If you have some control flow here that depends on data, then you will be able to see it as well. And so, yeah, basically that's all we need. That's the representation. And so with that, we can represent basically the vast majority of optimizations done today. And in terms of languages that we feed in, right, we have Python, as I mentioned before. That's our main kind of entry point into the language because we wanted it to be very kind of scientific computing forward. We have also languages that are based on Python, and also kind of other languages, including C and Fortran, right? So we really want to try to take those languages, and not by any form of magic, we want to take them into this representation. So this is a kind of a multi-step approach. We take the code, and then we run a few, kind of pre-processing steps that makes it more amenable. Just going to give you one example here. That basically a method. So object-oriented programming, a method is like a function with an object attached to it, right? Here, a method is a free function with all the basically data that it's touching attached to it. So that's the way we see the things. And then that allows us to compile kind of interesting code. Not all code, but most code. Then we have this representation that is the initial one, and then it undergoes a few coarsening passes to simplify basically the control flow and keep it more data-centric. So that's what we end up here with. We really take this original application and turn it into something we can work with and then optimize. And the optimization, really, that's where all the fun is, right? So we have things where we can modify parts of the graph with different, kind of patterns that you can write once and apply in other applications as well. We have, if you don't know what to apply or where, we have a Visual Studio Code extension that shows you static and runtime analysis of your code. And we can do some tuning on it. And we can even, that was recently added, so it's still experimental. We have some heuristics that will get you basically to a very good starting point. Like, so essentially expand all the parallel regions and try to increase that and decrease data movement, but not really going too far. So there is always room to go further and kind of go with the cycle and keep optimizing. And so just to kind of show you what this looks like, this is really the Visual Studio Code extension that we have. Can truly go click transformations, see where they apply them with conditions, see what happens to the code, rerun it again, see the performance. Again, this is the kind of workflow we're trying to support, right? And on the left-hand side, the code doesn't change. So in that sense, really, we were trying to kind of understand and improve the workflow. Again, this is a research project. We don't even know if this is the right workflow, but we're definitely looking. So what we're working with the users is definitely trying to understand how to get this better, how to make this easier. And so, yeah, so I mentioned a lot about this language, but I didn't mention how it really maps, right? This is the GPU kind of workshop, right? So we take this code, and basically that's not the whole story. So each map here, each parallel scope, we can attach a schedule to it. Where do we want to run it on? And then each array here, we can attach where we want to store it. And that already kind of this kind of minor difference can allow us to run with heterogeneous programming, right? So we now have nested parallel scopes. So if this is CPU, okay, the multi-core map here becomes an OpenMP loop. The single core map becomes a normal loop. But if I wanted to make this into a GPU program, what would normally constitute like a whole program change, right? We would have to rewrite everything, is now a simple transformation that just adds an array here in between, says it's on the GPU. The edge here in between those two arrays now becomes a memory copy. And we change this to be GPU device schedule. This automatically changes to block, and then we get completely different code. And so to me, that's one of the most interesting parts about a representation like this. You can just easily change the language or the target, right? And we do support a wide variety of targets. So different CPUs and both kinds of GPUs and FPGAs and distributed libraries, essentially. So you don't have to write MPI code. It's, again, an edge. It's an operator, a library node that says all reduce, things like that, that really kind of makes it easy. Yeah, so we have been using DACE at SPCL for a while now. It's been a major vehicle for us for research and trying to optimize real applications. So if we start with small benchmarks, we have NumPy Bench. That's a really excellent project with 52 different scientific computing applications written in NumPy or Python. By the way, if you do have QCD applications that you want to add, we will be very happy to accept those. So this will be very interesting. We want to kind of widen what we have in terms of applications. So yeah, this is supported, CPU, GPU, FPGA, distributed. I'm saying it like it's nothing, but you rarely see actually a work that does all of this at the same time. So that's kind of neat. If you take every other Python compiler out there for GPU or for clusters, we outperform it just because of this data-centric representation. So rethinking the program as a data flow and having the analysis done on the data flow level just works. Yeah, so graph analytics and other C programs and distributed tensor contractions is really nice, but that's not enough. We're talking now about real full applications. So unstructured hydrodynamics. So this is a Lulesh application where basically what we did was we took the original C code of Lulesh, and without any parallelism hints, we managed to outperform their own reference parallel implementation, just because we found a different way to parallelize it, or we found a better data flow. And we actually see a lot of times that because we reorder the code, or we reorder for data flow, it actually helps really nicely. Weather prediction I'll get to in a bit. And quantum transport simulation, so this is an application from ETH, really interesting one, been worked on for years, been optimized for clusters, worked, for the longest of time in a certain way, really, truly, twice ACM Gordon Bell finalist. And our PhD student looked at it, like from the data flow perspective, we basically put it back in Python, and he saw that the memory being moved here is too excessive. And so he said, okay, let's flatten those and let's retile this in a different way, something that may look like a mess, something that may be a complete rewrite, but it was 140 times faster than that previous implementation. So we ran it up to like 27,000 GPUs on almost the full Summit supercomputer, 60% utilization, really well, just from a Python code that was optimized here. So yeah, so that's that for just standard applications, but I really am here to talk about scientific computing and machine learning. Right, so I wanted to say, let's apply what we know here to deep learning, right? So why can't we take the deep learning problem and reformulate it as a data-centric program, right? So why can't we just take a PyTorch code, add a decorator on top, and then try to understand what's going on inside and try to optimize that? So that's what we did. So it was a really nice work, really ongoing work, right? Because it's working very well. So the idea was here not to do anything that is operator-centric. In fact, most of our operators are written in NumPy, something that looks like this. And we also don't have to write the backward pass because we redesigned symbolic auto-differentiation to work directly on the data flow representation. And that allows us to do further optimizations that no other compiler can do, which is kind of nice. We, instead of being very manual, we try to go down the heuristic path here, try to automate the pipeline, but still allow the guided approach to kind of finalize the thing. And so, yeah, so we take this PyTorch code, we load it as a graph, and we apply, you can, because we use this open neural network exchange representation, you can use other frameworks, but we only train with PyTorch. And then we undergo a certain set of steps. Okay, so kind of this optimization pipeline, starting from high-level optimizations like, kind of algebraic, einsum optimizations, going lower to kind of doing different with this automatic symbolic automatic differentiation. We can do different optimizations before and after we differentiate, which allows us to outperform all the other compilers by large margins, especially for operators that are not well supported. So this is MISH, this is used for object detection. I imagine for scientific computing, this is just as useful, right, in that sense. And then we go and do some data layout tuning. And lastly, we can specialize to hardware. So as I said before, we can do a lot of optimizations in this representation. One of them is to kind of fuse everything and use warp level intrinsics because that's the data flow, even at the cost of replicating computations within. And so all in all, this leads to an interesting set of performance results on a wide variety of networks. We have 12 in this paper. And, some of them well optimized, right? Like ResNet 50, we match, but others, especially the less well optimized, we always kind of outperform, and that's really interesting. And the fact that I said in the beginning with the 2x, right? So we're actually the closest to twice the performance. And when we want to go guided really on these very well optimized networks, so one is a transformer, another one is a convolutional network, we actually went through the pipeline and then kept going to do some guided optimization. And actually a bachelor student who was working with us at the time, he just found a new fusion opportunity, right? So he's the lead author here of this paper. He just looked at the Visual Studio Code. He saw, oh, wait, I can fuse this convolution. Because we escaped the library jail, we can now do optimizations further beyond what the others could do. And so, yeah, that was that. And the remaining time, I really want to kind of touch on a more scientific computing application, but a full one. So not like a micro app. This is a collaboration with CSCS and the Allen Institute for Artificial Intelligence. And so this project is really ambitious and it's really interesting. So I'm going to present this at Supercomputing very soon. And the idea here is to really make the whole weather model run in Python. So essentially you call this Python-M with today's weather and you get tomorrow's weather, or something like that. And really not a single line of Fortran. And the idea is to take this model, which is this FE3 climate model, run it, distribute it, and to kind of compete with the Fortran production implementation, really the one that was optimized for CPUs. We want to run it on GPUs, right? So this full thing actually is 40% of what it used to be when it was Fortran. So it's only 12,000 lines of code. And then we support this by GT4Pi DSL, and we try to kind of compare with that production Fortran. And the code looks mostly like this. Again, we do have control flow, but it is usually coarse-grained. We have some if conditions above, a certain section of code or something. And then we have the stencils written in this domain-specific language, which is kind of nice. It has a lot of, kind of relative indices and so on. This whole thing is part of this big model, which has like 19,000 stencil calls. And in the end, we just take, this loop that runs over the dynamical core, and we plug the decorator on top of that. All the 12,000 lines then get processed, compiled, SO file, and we run. Now, of course, when we actually want to look at this representation, this is way bigger than what we can imagine, right? So this, I don't know if you can even see this. This is the program. If I zoom in, this is still the program. This is one tiny part of the program. It's still big. If I zoom in further, this is still the program. And even if I look into the individual tasklet, it's very big. We're not going to do this manually. We need something hybrid. We need something that we can work with. And so the idea here was to automate the pipeline. So you see the blue parts here, they are manual. Yellow parts are automatic. We really try to expand how much we can do with automatic. So first thing is we determine computational and data layout for the characteristic stencils. We just, kind of optimize specific stencils and see what we want. And then that's kind of a heuristic for us. And we really treat data seriously, right? Even the padding, we have post and pre-padding just to make sure everything is aligned. It's very interesting. Then we auto-tune. We auto-tune locally. We try to take those results, try them globally. Really kind of an interesting thing. And then, that's the fun part, right? We get back performance results. And we actually auto-generate performance models because we know the data movement characteristics of the program. We know how to compute if it's doing a peak memory bandwidth and how much of it it's doing. We know how to rank by the total time that each of those stencils take, because some of them actually called multiple times. Then we know to see that something doesn't make sense here. That's now a human thing, right? Now we need to inspect some kernels. And so in this Smagorinsky diffusion here, for example, we saw something that didn't make sense. Smagorinsky diffusion is very simple. It actually looks like this. And then we found out the Fortranism that caused the reason for this slow performance, right? So the star-star operator, right? So the 2.0 here, okay, that's fine. We can convert that to del PC times del PC. What we didn't think of when we first wrote the system was that people are going to do power of 0.5 for square root. We replaced that. We made a pass. Now it applied everywhere in the code. And now we're at 100% performance, right? So that's kind of an interesting thing. And that's how we applied it. And we did multiple cycles of this. And we ended up with performance that was actually 4 times faster than this implementation, all in Python, okay? Running up to 2,400 nodes. All in all, 6 weeks of work, 10 changes to the SDFG, like this intermediate representation with 4 performance engineers. Depending on the GPU, if it's A100 or P100, we actually get up to 8.5 times speed up. And we never changed the model code. That's the important part, right? We never changed the thing that the meteorologists are going to then adapt later on, right? These are all generic passes. They can adapt this. They can change and take a different model, right? So to summarize, okay, my claim and many other people is that data movement is all we need, right? What we need to optimize, right? Second, we try to make a model and workflow based on that, run it on a wide variety of applications, machine learning included, and real scientific computing to show that really we can support the performance engineer in the middle. And who knows, maybe the future is going to be nice for all of us machine learning enthusiasts and performance engineers and scientific computing domain experts. And so yeah, so they obviously it's completely public. Everything we do is public, so you can just go ahead and try it out if you wanted to. But yeah, thank you.
Thank you very much, Klaus. Very pleasure.
Thanks for the nice talk. So I have a fundamental question. It seems that there are a lot of opportunities of optimizations that performance is lost because of the complexity of the code, the way it is layered in high performance computing, and so on and so forth. And I think this approach is very nice because it allows to get high productivity and at the same time high degree of control on optimizations can be performed. So that's nice and easy. Well, easy, no, nice and clean. But the question is, are there some kernels that are fundamentally bound, memory bound or data motion bound? You know, like, for example, there is a lot of talk about conjugate gradient to be used as the next benchmark for high performance computing because LIMPAC is not realistic anymore. So is it, and I'm not an expert in conjugate gradient, so I'm asking you, is it something that is fundamentally bound for which there is no hope to use days to solve it, and then we have to devise new hardware and so on, or it's a similar problem? So is there fundamental memory boundedness of some applications, or is everything can be solved by just rewriting the code in the right way?
Yes. So specifically, thank you. Excellent question. So conjugate gradient actually is one of those applications that, well, the algorithm, the standard algorithm has this bottleneck, right? At some point, you're going to have to do this this kind of reduction across everywhere, and that's the part that doesn't scale. In the end, there will be algorithms that fundamentally don't scale, and the problem with these benchmarks is that there is a limit to how you can change the algorithm, right? So how much you can change, right? How much leeway you have. If you could change the algorithm, maybe there are other ways, there are better ways, right? So maybe not even conjugate gradient, maybe you would find a different solver that just does the work better, right? So at that point is kind of the between benchmark and actual performance engineering, right? Because at some point as a scientist, you might say, I actually would like to use another algorithm because it would be better for me, more numerically stable, faster, any kind of reason. So at that point, I think that also the optimizations will not, we cannot magically change or transform the code, but we can say where the bottlenecks are. And that's one of the things we do say. So because of all this performance modeling, we try to also pinpoint what things cannot be resolved with the system. Maybe we don't display it, in the best user-friendly way to say this is the end, because there might always be some way to kind of improve. And this is really an open question. But yes, we try to resolve that by just showing to the user that there might be a limitation here, right? So I hope that answers the question. Go ahead.
Yes, I had a related question to look at because so you demonstrated the performance improvement for the solvers. I was wondering whether it's a sparse solver or solver for sparse matrices, or so which is exactly the one. So you had a table at some point where you improve on Python written applications, and then there was a line which said improvement of the solver. Yeah.
I see. So this was a category of very simplistic solvers. Mm-hmm. I think that it has a certain Cholesky, I think a few versions of Cholesky, a few versions of value decomposition with different, pivoting schemes, if I remember correctly. And so those are kind of, again, benchmark applications. Where do we improve there? Well, it depends on who we improve over, right? If we improve over Python, then of course Python is an interpreted language. There is only just compiling the code has a certain gain over that. However, I can say that we also have improvement over compilers that compile Python in another way, right? And so the reason we improve there is because we can create schedule changes that minimize data movement, right? So in that sense, if you did the for loop in the wrong order, or you even laid out your data in a suboptimal way, we can still get speed up, even though we don't change the algorithm. Now, there are other things we do like tiling, for example, and so on, that also help performance. But in that particular case, those were schedule changes because those were the heuristics that I mentioned before, the automated heuristics, and they try not to do too much. They try to tile reductions. I mean, that's the only thing they try because they want to avoid atomic operations. Especially on the GPU, that's something you really want to avoid. So that's something we try to do automatically. But yeah, I mean, we didn't go too far there. I know that we can improve further.
All right.
Yeah. Mm-hmm.
Okay. Are there any other questions in the room? Bartosz, and then let's have a quick look at the Zoom as well. We'll try to stay on time, so maybe.
Thanks a lot for this nice talk. So again, a related question to the two previous questions. You mentioned that you do a lot of fusion to improve utilization. What about thinking about inter-node data movement as well as global reductions? Do you do automatic pipelining and stuff like that?
So yes, that's a great question, because that's one of the things that we showed there was distributed performance. And there, the fusion for us, it doesn't matter if it's across, between collective operations or between global memory and registers, right? So in that sense, yes, we have transformations to automatically transform sequential code into parallel code and parallel code into distributed code based on MPI. And there we use the same things. We have transformations that, for example, take gather followed by scatter or things like that. And we see the data movement characteristics and we just remove them if we know they're not necessary. So pipelining, that's, I guess, something we can take offline because we are under time constraints, but there are different forms that we can apply. Yes, so double buffering, for example, is a nice transformation that we have. We actually apply it twice on the GPU matrix multiplication example that we have. We apply it once on shared memory and once on registers. Then we can outperform cuBLAS. And so that's kind of an interesting thing. So same transformation, apply twice, different results. Yeah. Mm-hmm. Thank you.
Really exciting. Are there any questions on Zoom? Can you double check? We don't see any. Maybe just last and a very quick one. So you chose Python, and I mean, we do have some applications written there, but most of our lattice QCD applications are written in a C or similar, but what we've experienced is that when comparing Python and Julia straight out of the box without any optimization, Julia is faster. Why did you choose to work with Python in particular?
Exactly for that reason.
Okay.
Python is such an amazing language. It's more than a language. It's an ecosystem, right? It's everything. You can plot your results. You can do, you can save it. You can load file formats directly from other representations. You can download them from the internet, right? And that is the language we want to optimize. Julia is already compiled. And we actually asked around. We tried MATLAB for Octave. We have a front end for that too. And we converged very quickly on Python because that seems to be the trajectory of where scientific computing is heading as well. So yeah.
Makes sense. Excellent. Thank you very much, Tal. Let's thank the speaker again. And our next talk will be over Zoom. So just give us a minute or two to set up, and I will announce the next speaker, who is joining us from California.
Morning, Marina.
Hi, Kate. We will just need, should I load the slide here, or are you able to do it there?
Oh,
no.
Hopefully you can see them there. I haven't uploaded them anywhere yet.
Excellent. So we can see the slides. They're not yet full screen. And now,
are they full screen?
Yes, now we can see them full screen. We are running a little bit ahead of the schedule. Are you ready to start? Should I announce you?
Sure. Just one screen check. On the right-hand side, is the Zoom panel covering some of the slides, or can you see the full slides?
We can only see the full slides.
You can. Oh, that's fine. That's fine. Okay.
Yeah.
I just was curious. There's no Zoom isn't obscuring the slide at all.
Could you please say that again? There is no Zoom.
Is Zoom obscuring the right-hand side of the slide?
No, I think we can see the full slide. There is no.
Okay. I'm good to go whenever you are then.
All right. Well, it's a pleasure to have here with us, albeit remotely, Kate Clark. Kate is a Lattice QCD native, if I can say that. So Kate is a distinguished technology engineer at NVIDIA. So before joining NVIDIA, Kate worked at Harvard University, Boston University, and Columbia University as a postdoc. And also Kate has a PhD from the University of Edinburgh. In Lattice QCD community and HPC community, Kate is well known for authoring CUDA library, about which we will hear quite a lot over the next days. So this is the a reason for most Lattice QCD efficient usage of GPUs to date. So the CUDA is a highly optimized library designed to enable legacy Lattice QCD. On LinkedIn, it says application, but I would say nowadays applications. So many Lattice QCD applications are now able to run on GPUs thanks to this library authored by Kate and her collaborators. So without further ado, Kate, please take the way. We are looking forward to your talk.
Okay, thanks, Marina, for the introduction. So today I'll be discussing some of the computing challenges that LatticeQCD faces as we are now in the exascale and maybe even consider going beyond the exascale. I'll keep the sort of discussion in the more general sense rather than focusing on the details of LatticeQCD for the sake of the general audience. So I'll start off with an introduction to what we're talking about today, discuss a little bit about GPUs for LatticeQCD, discuss the scaling challenges that QCD has and how we'll tackle them going forward into the future, discuss parallelism and locality, and then finish up with some brief discussion of future challenges at the end. Okay, so let's start off with an introduction. So, for many of us, even those who are not familiar with LatticeQCD, as intimately, many of us will be familiar with it in terms of how much compute cycles it uses on supercomputers, and that statement, throughout the world, whether Europe, America, or Asia. QCD is very hungry for supercomputing cycles, and you can see this in the breakdown pie charts here. The plots on the left, charts on the left show the percentage of how much QCD is used on the the Summit supercomputer from 2019. And you can see, although QCD was only allocated a sixth of all the compute cycles in the dark blue there, it actually took up more like a third of all the compute cycles. And that's similar seen at NERSC on the right here. You can see in 2017, for example, QCD occupied around a fifth of all the compute cycles. So QCD is a very computationally hungry subject. And because of that, we need to understand how to make it more efficient, as efficient as possible, if for nothing else, to give more compute cycles for everyone else. So what is LatticeQCD? So, for the two-slide summary, quantum chromodynamics is a highly nonlinear theory. We cannot solve it directly, so we resort to numerical methods to make predictions. So the infinite spacetime, four-dimensional spacetime, becomes a discretized spacetime on a four-dimensional periodic box. The continuous valued PDEs become finite difference equations on this hypercubic grid, and these PDEs are now represented as linear solvers in the simulation. So we're solving sparse matrix systems, AX equals B, which is a prevalent computational paradigm throughout HPC. So as I just noted, QCD consumes 10% plus of public supercomputing cycles. And over the last 30 years, the QCD community has a history of highly optimizing their code for every new HPC platform that's come along. And the scale of the jobs, in current supercomputers that are built using GPUs, often jobs will run up to 1,000 GPUs in size. Now, there's two main steps in LatticeQCD calculation, speaking in very broad brushstrokes. We have the so-called gauge generation phase, and the second phase is the analysis phase. Now the first phase is essentially a Markov process. So you have a serial Markov process. The only source of parallelism in this step is the underlying grid parallelism or data parallelism of the problem. You have to strong scale the problem over as many processors as possible, over as many GPUs as possible. The most computational dominant routine is the Krylov solver, so the AX equals B problem, where the A comes from the discretization of the Dirac operator. So we discretize the Dirac operator, becomes a stencil on the grid. That's the sparse matrix system. Most of the computational cycles is spent there. The analysis phase is where we consume all the ensemble of configurations generated in the Monte Carlo phase in step one. Again, the Krylov solver is the dominant computational routine there. Unlike the first phase, we don't need to strong scale because we have an inherent data parallelism. We have an inherent task parallelism. All the configurations from step one, we can parallelize over that. And so it's not so challenging from a strong scaling point of view, but it's a computationally large, very expensive. And so we have to spend a lot of cycles on both these steps here. Now, QCD is a very expensive domain. We've, as a community, we've spent many years trying to categorize the computational scaling cost of the problem. In many ways, it has some exponentially bad scaling. the problem gets harder as we increase the simulation size, as we increase the simulation fidelity. So we decrease the lattice spacing on the grid and reduce the quark mass, which is the theory of one of the underlying Bayer parameter, which goes into the sparse matrix, which describes the interaction of fermions. As that quark mass gets smaller, the computational cost gets harder, and unfortunately, nature is a small value of the quark mass. So we have this pathologically bad scaling in all these three parameters: the volume, the lattice spacing, and the mass. And the community collectively describes this as the Berlin Wall. As you go towards reality, large simulations of small lattice spacing at small quark mass, the computational cost was equated to trying to scale the Berlin Wall. Now, there's been lots of effort, to scale that Berlin Wall, to reduce that computational cost, and you understand where does this pathological scaling comes from, whether it's with respect to the volume, whether it's with respect to the cost of the linear solver, whether it's the cost of driving the Monte Carlo simulations. And there's been much progress over all these different areas. And so for using for linear solvers, for example, we use multigrid or variations on multigrid to reduce the condition number dependence in the linear solvers. And there's dozens and dozens of papers over the last 20 years, 30 years to reduce the computational costs, but the costs are still very large. For the one I'd like to highlight at the bottom here is just the autocorrelation cost as the lattice spacing goes to zero, the topology of the simulation. So the simulations effectively freeze, your autocorrelation lengths diverge, and that's still essentially an unsolved problem. So although there's been much progress over the last 20 years, there's still extreme computational challenges in QCD. And that's before we actually get to trying to put the calculations on the processors for efficient simulations. So let's turn to actually doing, using GPUs for lattice QCD. So I don't need to describe what a GPU is, of course. We're all familiar with GPUs nowadays. They're very extreme hierarchical processors. We have many individual processing elements on a GPU. On an NVIDIA GPU, you program these using a Cartesian hierarchy of grids. This abstraction is called the CUDA abstraction. You have a deep memory hierarchy going from very fast and low latency registers to very high latency and very slow host memory on the CPU. One interesting thing that's happened over the last few years is there's an increased instruction hierarchy as well, not just the memory hierarchy. Recent NVIDIA GPU generations have introduced this concept of tensor cores, which are highly coupled instructions catered for doing matrix multiplication. You have the regular CUDA cores, which do the standard floating point operations. If you want to consider this in the hierarchy sense, you can even think about atomic operations as being the least coupled operations. Now, synchronization is possible at many levels of this hierarchy, whether it's within the warp, so that's the moral equivalent of the SIMD unit in the GPU, at the thread block, where groups of threads or groups of warps act together on the same processor in the GPU, at the grid, which is the entire GPU, at the node, obviously, just each node of all multiple GPUs in a node, and of course, the entire cluster. Now, since I work for NVIDIA, it's my job to introduce, whenever we launch a new architecture, I have to tell you all about it. So here's my the one marketing slide here. So we just recently announced the H100 GPU. That's the NVIDIA Hopper GPU. So the Hopper GPU is the latest evolution in NVIDIA GPU technology. Of course, it's faster than the prior GPUs before. One interesting thing I'd like to highlight is the hierarchy of precision and performance that we have on GPUs today. So you can see here in the first bullet here, we have from floating point 8-bit precision all the way to FP64, which you're more familiar with in HPC audience. Moving from FP64 to FP8 corresponds to a significant increase in raw teraflops performance, and that, of course, is not surprising. Low precision is cheaper to make much faster. It's much more energy efficient to make much faster. And this trend is seen throughout the industry. So being able to make low precision much faster, and this is driven by the AI machine learning audience who only require low precision. But the important thing to note, in terms of the grand big picture, slowing down of Moore's law, etc., is that it's much cheaper and much more efficient to make low precision much faster for much less cost in terms of area. So this is something that the community as a whole has to deal with going forward. And being able to use these low precision flops will be significantly any application that can use these low precision flops, even if they weren't originally catered or developed with this in mind, will get a transformative speed up. So this is disruption in the community, and being able to use this being able to utilize this disruption will bring great advantages. So all the work I do is on a library called CUDA, at least all the work I do with respect to QCD. So CUDA stands for QCD on CUDA. It's an open source library available on GitHub. So this started off as a library when I was a postdoc many years ago. So it seeks to bring GPU acceleration to lattice QCD applications, so such as BQCD, Chroma, CPS, Milk, and many others, maybe OpenQCD soon. So we seek to maximize the performance of QCD simulations using techniques such as mixed precision methods, using auto-tuning, using optimal solvers, so multigrid typically means in the case of lattice QCD, improving strong scaling using technologies such as NVSHMEM or one-sided communication. CUDA is now even portable due to being open source, and it's a community effort. It's now been ported to other architectures. So it's not just exclusively the domain of NVIDIA GPUs, it's also available for HIP, SYCL, and OpenMP at the moment. Or the OpenMP is still in development, and SYCL is a pull request in review, which is still undergoing some work. But for example, HIP support is there. So CUDA is if nothing else, it's a production library, but in my mind, what it is a research tool for how to reach the exascale and go beyond, how to map this hierarchical computation onto the hierarchical processors that we have today. So many folk have contributed towards CUDA over the years. Let me just shout out to my collaborators, and in particular, in green, I just call out my collaborators at NVIDIA who work on CUDA with me. So since we've been working on CUDA, the GPUs have got faster, obviously. From 2008, when we first started working on CUDA, what we're showing here in the green bar charts is the raw performance in gigaflops of the stencil kernel in CUDA, so the so-called Wilson stencil. This is the standard sparse matrix vector product from QCD. Now, what you can see is, the raw performance, the green bars, has got faster with each generation of GPU. Nothing surprising there. We're starting off the original Tesla GPU, moving forward to Fermi, Maxwell, Pascal, Volta, Ampere GPUs in this plot here. I think I missed off Kepler there. But what's more important is what's the actual throughput of science? What's the actual application speed up? Now, that's what the black line is showing on this line here. Now, the important thing to point out is the black line is on the logarithmic chart, on the logarithmic axis on the right-hand side, and the green bars are just the linear axis on the left-hand side. So although, we're seeing, the expected improvement in raw performance in the green bars, what we're actually seeing is more than an order of magnitude in actual algorithmic speed up or science speed up because of the investment through software and coupling of the application to the underlying hardware. So examples is, so here we started off in 2008, we added multi-GPU capability, we refined our mixed precision techniques, we've added multigrid, we've optimized the multigrid, we've using a new multigrid variant called deflated multigrid. So this combination of our multiplicative speed up through algorithm meets machine is really where you get the optimal science, science speed up. And that's where all the effort is. So how do we map this sparse matrix problem to the GPU? So the sparse matrix problem, the finite difference operator, the stencil, if I use all the different labels you could call this thing, is called the d/ in lattice QCD. So, it's a regular hypercubic lattice. So implementing this in a GPU is fairly straightforward. We have one space-time point per thread on the GPU. If we have, a volume, for example, of 24 to the power of 4, that's plenty threads to saturate the GPU. So we've got, hundreds of thousands of threads to saturate the GPU. Then each thread, what it has to do is loop over each direction of the stencil. We have a 4-dimensional problem. Our stencil connects nearest neighbors on that grid, forwards and backwards. So we have 8 directions we have to load from, load the neighboring grid points, load the stencil coefficients that connect those 2 sites, do the computation. So it's a small matrix times vector operation, and then sum those numbers together and save the result. It doesn't take much to work out. This is a very memory bandwidth bound operation. So the arithmetic intensity is about 1 in single precision. So what we have to do is reduce the memory traffic at all costs. So what we do in CUDA is we do, a compression where possible. So QCD has this many symmetries, and so we can use those symmetries to compress the underlying data. We can also use mixed precision solvers, so go all the way down to 16-bit data representation to minimize the memory traffic. And when you implement this in a GPU and crank the handle and look at the performance, nothing is that surprising here. The performance is exactly as you'd expect. Lower precision equals higher performance. So you can see here that single precision is double the performance of double, and half precision is double the performance of single. That's just a statement of your performance in terms of gigabytes per second is mostly invariant, which means that the flop's performance goes up as you lower the precision. But what you need to do, of course, it's all fine and well reducing the precision and reducing the memory traffic, but if you don't put the algorithm together in a sensible way, you won't get the precision out of the final answer. So in a mixed precision solver, there's many ways you can use this low precision. On the plot on the left here, I'm showing the time residual history running conjugate gradient algorithm through the MILC application, where I'm using quite a light fermion mass. That means a fairly badly conditioned linear system. You can see if you use this in a naive fashion, it's very easy to have a very large number of iterations in your solver and never even converge. But when you're more considered and put the right things in high precision and are careful how you put this together, you can actually get a very good speed up with a small overhead and increase in iterations, and the actual application gets a good speed up doing most of the work in half precision. What we actually use is multigrid. Now we use multigrid for multiple reasons. It's a bottom line, it's a faster algorithm. It's a more optimal algorithm. You have effectively condition number independent convergence. You have volume, sort size of the problem independent independent convergence, and it's a much more stable solver. When you actually run multigrid, because you're solving all error components equally, all frequency scales, you know that you're solving the low frequency error components just as well as the high frequency error components, which means that you can actually trust the results you get out, unlike with conjugate gradient. Now, multigrid is a very hard problem to put in the GPU. The GPU is is very different than the CPU. A CPU has a small number of threads. It's optimized for low latency. A GPU is very different. You have many, many threads. To hide latency, it requires many threads to run in parallel. So, in multigrid, that means the fine grids. So the original problem will run very well on the GPU. But when you go to coarser and coarser descriptions of that fine grid, when you restrict the problem down to smaller and smaller problems, you end up with potentially the worst possible scenario. You could have more cores, more processing cores and degrees of freedom. You're going to be more serial and latency bound, and the coarse grids will become the Amdahl's law limiter. So what we realized what we had to do when putting multigrid in the GPU is you have to extract every source of parallelism that the problem has. So, a naive implementation is just going to use what I'm calling grid parallelism. So we've got the underlying grid of the problem. So one thread per grid point, like what I described a few slides ago for the D slash. But if you've only got a problem size of 2 to the power of 4 in the coarse grid, that's not going to be enough to saturate the GPU. What you need to do is look at all the internal sources of parallelism. So in QCD, each grid point, the nature of the stencil is actually a small matrix vector product. So what we have to do is we have to break that matrix vector product up and split that up between threads. We've got a 4-dimensional problem, forwards and backwards. We have to grab neighbors. So we have to split the act of fetching the neighbors in the stencil between different threads to expose all the parallelism. And we've even gone to the level of splitting up the small dot products, which compose of the matrix vector products. So there's lots of sources of parallelism, and we have to uncover all sources of parallelism to be able to saturate the GPU or come close to saturating the GPU such that the coarse grid problems are no longer the Amdahl's law limiter. So in the demonstration here in this slide, we started off with a lattice size of 10 to the 4, going all the way down to 2 to the 4, and we're looking at the performance in gigaflops for these different parallelization strategies. And as we go to a smaller and smaller problem size, we see that we have to uncover every source of parallelism in the underlying theory or on the underlying discretization in order to saturate the GPU. So in the coarsest grid, the naive discretization, the naive parallelization has 16-way parallelism, 2 to the power 4. Whereas if we uncover all this hidden linear algebra potential sources of parallelization, we can go up to 25,000 way parallel. And that's critical to make sure we're not Amdahl's law doesn't kill us within the multigrid solver. So when we put this mixed precision methods together with all this fine-grained parallelization, and couple that to running on new machines, we see significant throughputs in acceleration of QCD simulations. So in this plot on the right-hand side here, I'm showing the baseline, which is running what we call like classical Krylov solvers, so conjugate gradient type algorithms. I think in this case, it was domain decomposition preconditioner with a GCR alter solver running on Titan supercomputer, which is 2012. We can run in the new supercomputer, keeping the algorithm fixed, that's blue to red. We get a doubling in performance running on an eighth the number of GPUs, so 16 times or 17 times gain if you put the numbers together. But then if you couple that with running on this new algorithm, you can see that's where the real gains come from. So machine times algorithm, equates to 100x speed up or 100x improvement in throughput. So going from the original Titan run, which was done in 2016, through to running on the latest A100 clusters, we see significant improvements. And so this is really critical to couple this improvement in machine evolution and algorithmic innovation. Just to highlight the mixed precision techniques used here. So we've got double precision on the outer defect correction. The actual Krylov space is done in single precision. The multigrid preconditioner is done in half precision. And we even incorporate some integer precision operations in here just for reproducibility and determinism. So adding integers together is associative, but a floating point is not. So if using atomic operations, we use integers to make sure that we have reproducibility. So, we can do all those algorithm tricks, but there's still many scaling challenges in QCD and HPC in general. What a node looks like has evolved a lot over the last few years. So on the left-hand side, we've got 2007. This is a Cray taken, I guess this is something like the Jaguar supercomputer, something like that. So, a single node was very simple. You have an Opteron processor or like 1 or 2 cores. You have one network connecting everywhere. It's flat memory space. Today's supercomputers are rather different. You've got multiple GPUs in a box. You've got a network between those GPUs. You've got multiple CPUs in the box. Each one of those CPUs is multi-core. You've got many different. You've got a network between those nodes. The node itself is very hierarchical. You're not even sure what a node even means anymore. Whether is it this entire memory space here, or from a programming point of view, it's sometimes more convenient to think of the GPU as being the node. And the GPU hierarchy is evolving into itself. So looking at 2006, which was the first CUDA GPU, which was the NVIDIA G80, which is the original Tesla GPU, that was 681 million transistors. This latest GPU, the Hopper GPU, over 18,000 FP32 processing cores, 80 billion transistors, but one SM, so one processing element, one streaming multiprocessor on the Hopper GPU is equivalent in transistors to the entire GPU from 2006. Because of that increase in scale of the GPU, we've had to introduce a new level of hierarchy in how to program a GPU. So we've always had the ability to communicate between threads in a warp, threads in a thread block. So threads in a warp is threads within the moral equivalent of the SIMD. The thread block is all the threads running in a group together on an SM. the global is, the global system is just, the entire GPU being able to communicate through global memory and synchronize when a kernel ends. But because of this, extreme size of these GPUs, we've had to introduce this new level hierarchy, the thread block cluster, which allows us to do communication between groups of SMs. So the hierarchy within the GPU is, scaling out as well. So hierarchy is something we cannot ignore, and we are going to have to consider, increasingly as we go forward. And as GPUs evolve and as science evolves as well, we have to evolve the science with this hierarchy. Now, going back to the QCD problem at hand, we can parallelize this problem, put it on multiple GPUs. Now, the standard way of doing this is that we, do domain decomposition. We have a regular hypercubic lattice. We're going to give each GPU or each processor a different subdomain within that lattice. And to parallelize that problem, we are going to run on multiple GPUs using something like MPI. So the way of doing that, you'd have like a Halo packing kernel to generate contiguous faces to give MPI to do a Halo communication. While that Halo communication is going to go on, you're going to do the interior computation, which is going to do all the interior computation, which doesn't depend on the halos from the exterior, from process that are on different processors adjacent to you. Hopefully these two overlap, and if they don't overlap, you're not going to strong scale. And then finally, do a Halo update kernel. Now, this all works really well. Okay, I guess I have to speed up significantly because I'm not halfway through here. So in principle, this works really well on, when you're on relatively large local volumes, you can hide that communication. But when you strong scale, you get more and more white space in your profiler when you look at this. And what you see is, white space is bad because it means your GPU isn't working. The issue is not because of, the underlying lack of bandwidth in the system. The issue is because we have to synchronize with the CPU, and the task marshalling, where the issue of the communication is handling at the wrong memory space. It's handling at the CPU. So you have to synchronize with the CPU just to communicate data between pairing of GPUs, or even you have to synchronize the CPU to send data over the network. What we need to do is move that communication, or the task marshalling of the communication, to the GPU itself. And so one way of doing that is to use NVSHMEM, which is this new NVIDIA library, or relatively new NVIDIA library. It's been out for the last few years, which offloads that communication to the GPU itself. So instead of using API in the host, we let the GPU threads issue the communication. When we do that, we can have what we call Uber kernels, which do everything. So instead of having separate kernels for doing the packing, the interior, the exterior, a separate host process for doing the MPI, we now have a single GPU kernel which does everything. This minimizes the latency. All that white space goes away, and we get improved strong scaling. When we look at scale, what we see is strong scaling, the last QCD problem, going from small number of GPUs to many GPUs. The NVSHMEM technique is critical to reduce that latency and get better strong scaling. I think Matthias is going to talk about this later this week, so I defer details on this to Matthias. So let me talk about a little bit about parallelism locality here. So even without communication, we have to worry about scaling within the GPU. As we strong scale the problem size per GPU gets smaller, and we run out of parallelism. So you see here, we're decreasing the problem size in the GPU, and as we get down to 16 to the 4, 12 to the 4, the performance goes down, and that's because we don't have enough threads to saturate the GPU. Now, what we can do is we can batch, multiple sparse matrix vector problems together, which turns them into matrix-matrix problems as a result. So, turn a single Krylov solver into a batch Krylov solver, multi-right-hand side problem. So what we're seeing here is this is the improvement in performance as you batch together one of the stencil discretizations in Elastic QCD across different architectures. The more right-hand sides, the bigger the batch size, the bigger the performance. So we create parallelism and we create locality because we're getting data reuse, because we're turning sparse matrix vector into sparse matrix matrix. Multigrid gets, has the same issue, but even more so. Although as we evolve our GPUs going on this plot on the left-hand side here for Kepler all the way through Ampere, you see that in the large problem domain, so lattice length of 8 to the 4, 10 to the 4 in multigrid, you can see that we're scaling in terms of raw gigaflops, but the latency limited regime of 2 to the 4, where the multigrid solver will extend down to, isn't scaling at all because it's completely latency limited. So what we can do there is we can use multi-inside batching techniques to get significant speedups on the coarse grid. And there, the speedups can be more like 10x if you're starting from these tiny problems, because you're creating parallelism and you're creating locality, so more opportunities for data reuse. Multigrid itself consists of many matrix operations. What we realize is, multigrid is a preconditioner. We can use low precision there without worrying about convergence. All those matrix operations can be offloaded to the tensor cores, these highly customized processing engines in the GPU for low precision. Plot on the left-hand side here shows the multigrid setup kernels on the left-hand side, which are all matrix kernels. We can offload those to the tensor cores rather than running on the regular CUDA cores. The y-axis is logarithmic. Let me just point out here. So what we get is significant kernel speedups, 1.5x up to 10x performance improvement by offloading the matrix kernels to the tensor cores. So what we need to do is, enable this tensor corification, if you like, throughout the pipeline by batching the problem up. So all these kernels on the right-hand side here, all the kernels we were just looking at in prior slides, can be rewritten to use the tensor cores and get the speed up throughout the pipeline. If we were to do something like that, what we can do is we can take a physics pipeline, which is shown in this slide here. This is from one of the collaborations I work with, where we've got different, the workflow is, the workflow traditionally would be, calculate some eigenvectors, do some solves, do some projections. All of these operations, when done serially, if you like, are all have limited parallelism and limited arithmetic intensity, so they wouldn't scale well as we go to wider and wider and deeper processors. But if we do this batching transformation, it gives us the opportunity to increase the parallelism, increase the arithmetic intensity, and utilize these tensor cores where applicable. So that's the type of transformations that will need to be done to really scale towards the future. Now, hopefully I've got 2 minutes just to quickly finish off really quickly. So, probably many of us are familiar with a plot like this, which shows the, the trends in microprocessor technology over the last 30, 40 years, 50 years, I guess. What we're looking at is, the top line here, the orange triangles are, the transistors per unit area increasing with year, and this is Moore's law. This doubles every 18 months. Probably was originally 12 months, and 18 months, so it's slowing down more recently. What's happened is, single thread performance basically slowed down or stopped in 2008, and this led to a dramatic increase in number of parallelism through increasing cores on the chip. I won't dwell on this slide here, but because of this slowing down on Moore's law and everything, it comes through many core parallelization. Sorry, let me rephrase that. So we've had, Moore's law slowed down. We've had this transformation to many core, but because Moore's law is going to be slowing down even further, to really improve the scaling and performance going out, we've had this change over the last few years towards more specialized operations, such as matrix operations, and potentially even other tensor operations are going to be required to saturate the machine. That's true of the exascale, and that's true going forward to the zeta scale. It will be even more so in the zeta scale. Low precision goes much faster than high precision. This extreme parallelism is required to really saturate the machine, and we really have to consider hierarchy and locality to get the best of these machines. We could think of this as a bad thing, or we could think of this as a good thing. The positive spin on this is just, well, we have all these extra resources coming. If we don't use them, we're not going to scale very well. But if we do use them, there's potential here for superlinear speed up in science. So this is disruptive opportunities, and if we seize them, the science could go amazingly well. The other way of thinking about things, but with the lattice QCD spin on things, is we still have these fundamental underlying algorithmic challenges, such as the critical slowing down. If we have 100 times more compute, or even more specialized compute in the form of matrix algebra, does this allow us to really scale lattice QCD 100 times more fidelity? Well, it won't do, because of the exponential scaling of how hard it is. But another way of thinking about things might be much more advantageous. Other people in the community are looking at, machine learning based techniques for solving QCD problems. And, this evolution in machine architecture certainly might suggest that other approaches rather than this classical HPC approach will be ripe in the future. So let me just finish there, and I will open to questions if there's time.
Yes, there's still time. Thank you very much. Thank you very much, Kate, for this excellent talk. There is still some time for questions. In 5 minutes, we will have coffee served. So are there any questions for Kate? I don't see any. Let me ask one related. So you were talking about tensor architectures. So is there any way that CUDA could profit also from deep tensor processing units, or is this all specialized only for GPUs? I know that NVIDIA is making some in the future.
So this, I probably spoke past these slides a little bit quickly. So this slide here demonstrates some of that we've done already. So what we realized is that, I kind of skipped past this slide completely. You can, if you look at multigrid, for example, you can categorize the different kernels as being matrix matrix or matrix vector. So matrix vector isn't suitable for tensor cores. Matrix matrix kernels are. So what we've done is that we've re-optimized or rewritten these specific kernels that appear in the multigrid setup to use tensor cores. So what you're seeing in this plot here, going from the solid line to the dashed line, is the jump in performance for these obscure kernels here, which probably mean nothing to the general audience. But let me just say that these are important kernels in the multigrid setup that are some form of matrix matrix. And by offloading them to the tensor cores, they now go up to 10 times faster. So yes, we can utilize them. The key is reworking our pipelines to be able to utilize them more. So in this plot here, it demonstrates that we can up all of the kernels on the left-hand side. We can get tensor core acceleration, but it doesn't impact, which is effectively the multigrid setup phase. The multigrid solver phase, because it's a matrix vector type problem, it's not so amenable to tensor cores, and that's why transformations of the problem to a batch problem, which turns into matrix matrix, it would be a critical part of this enablement. So if we were to batch the computations, like in the slide here, if we batch the computations up, then you're getting them into a form where they can be rewritten for tensor cores. So there's lots of work to do there to do that. You've got to reorder your pipeline in the original application point of view to batch that work together, and then do the effort of actually optimizing them for the tensor cores. And so that's something we're doing in things like multigrid and other linear solvers. Other parts of the QCD pipeline, they wouldn't be, the analysis phase when you've got various batch contractions and things like that. They're not going to be suitable for these low precision tensor cores. FP16 is not so useful there, but we still have FP64 tensor cores. And so certainly one could use tensor cores throughout the pipeline. The main issue is just enabling it in the science application.
All right. Thank you very much. Let me see, are there any questions on Zoom? Roman, do you see any?
I think there was a question came from Hang Tong, but maybe there's a raised hand.
Yeah, actually, I have a similar question about tensor cores. So I was wondering that whether this tensor core can also be used in the gauge production, for instance, in the RHMC algorithm. Probably
I haven't thought of an obvious way to use it in RHMC. I'm happy to listen to ideas, but I haven't heard of I haven't thought of any idea where. I don't think it's directly applicable to HMC. So you could, so certainly the fermion forces, gauge forces, not so useful there. Going back to the fermions, the only way, sorry, the linear solves, the only way you could possibly use it there would be if you have enough pseudo fermions to extract, make it a big enough matrix problem. So the one exception to this is, so if you had like 16 pseudofermions or something like that, then maybe there'd be some way of doing it. One other place we have used the tensor cores is in domain wall. So domain wall is already itself a batched like 4-dimensional problem. You've got a 5-dimensional problem. The parts of the domain wall stencil are a matrix in itself. And so my collaborator Jushin has written a Schwartz preconditioner for domain wall, which uses tensor cores. So in that context, yes, we do have some aspects that can use tensor cores on HMC, but only for specific fermion discretizations. So there, what he's done is with the Schwartz preconditioner unto itself is not fast enough. Although it reduces communication, it's too expensive to use. And so what he realized was that if he rewrote it to use tensor cores, you could make it much faster, like twice as fast or whatever. And the speed up in kernel execution time was enough such that the algorithm was cheap enough to utilize, and it reduced overall communication. So it helps reduce communication, improve strong scaling, especially on machines that don't have good network. So in something like the Summit supercomputer Oak Ridge, which wasn't as well provisioned for network, it could give a 50% improvement in strong scaling there. So you could be doing 10x more compute, but because that compute is being done in tensor cores, it's faster in terms of time to solution.
So you mentioned about multiple procedural. Can I ask a bit more?
Since we're a bit short on time, can you maybe continue this offline? But we have one more question, which I assume goes in the machine learning direction. So Dennis, would you mind unmuting yourself?
Thank you, Kate.
Yeah, sorry for interrupting. So yeah, my question about actually future perspectives. You already mentioned the GPU architecture moving towards AI. So for example, the recent announcement of Hopper architecture. So NVIDIA, if I remember correctly, developed new type of kernels for transformer-specific neural networks. And it seems that, the usage of resources in neural networks is different than in latest QCD. So, we are more concerned about higher precisions. So how do you think, so basically, what are your thoughts about this?
So so transformer optimizations are really where FP8 comes from on Hopper. And I don't think there's any direct use for, so are you asking from a machine point of view or from the AI point of view in terms of, whether these transform model optimizations are applicable to QCD, or do you just mean they're all hardware FP8?
Yeah, so basically I mean development of hardware. So in the past we saw the increasing number of threads, number of cores, which in latest QCD it was very efficient. With every new architecture we had more and more performance. But it seems that now development moves towards more AI, and we will not see this trend anymore.
Okay, so no, that we will still keep seeing that trend, and I'll tell you why. So the green bars would be like the raw performance, and this is the thing that's improving with every generation. And you're perhaps worried that these green bars are going to start plateauing. That's not going to be the case. Although yes, there's more increased investment in AI-specific operations such as FP8. AI also requires a lot of memory bandwidth, and so no matter what we do for QCD, it's still memory bandwidth bound. So even if we, the Hopper GPU, for example, if we doubled the FP32 number of cores in there, it's not going to change the performance that much because you're primarily memory bandwidth bound. If we doubled the memory bandwidth, we'd get a huge speed up. So yes, we're having more investment in terms of transistor budget on low precision throughput, but that doesn't come at the expense of what we care about most in most of HPC, which is memory bandwidth. AI likes a lot of memory bandwidth, so that scaling is still going to continue. What it does mean is that we might not get the expected scaling in benchmarks like HPL, because more of the transistors are going to be spent on low precision matrix multiply, not on high precision matrix multiply. But for general HPC, for useful HPC, I might even say, if I'm going to be controversial. And the implication here is that HPL is not the most useful science benchmark. The scaling for actual science is going to keep going, even without using FP8 or FP16.
All right. Thank you very much, Kate, for this wonderful talk. Thanks for the questions, both to our local and Zoom audience. Before going to a coffee break, I just have one quick announcement. So the coffee break is served outside of this room. You will see it. And we also have an Axilera AI stand, which deals with AI hardware and software. So if you're interested, feel free to stop by the stand and learn more about our industry guest. All right. Thanks once again, Kate. And
thank you for
a round
the
of
invite.
applause for all the speakers of this session.
Okay, so I suggest we continue. Please also allow me to introduce myself. My name is Fritz Bayer. I'm a PhD student at ETH Zurich in the group of Nico Behrenwinkel. I'm also I'm an associate PhD student at the ETH AI Center. So just to give you an overview of what is coming up in the afternoon, we have 2 more student flash talks, and then we will continue with a panel discussion held amongst the keynotes, and also Marina, who actually jumped in quite spontaneously. And then Marina will give some closing remarks and we can all meet at the apéro. Okay, so we will start with a student talk that actually is online. So we have Dan Grau, PhD student at ETH Zurich in the systems group. Please, Dan, go ahead. We also will need to work on the streaming, so please bear with us for a second.
Can you see the slides? I'm streaming.
We can see perfectly. Thanks.
Excellent. Okay, so then can I begin? Is that okay?
Yes, please go ahead.
Okay. So hi everyone. Thank you very much for attending this talk, and sorry I'm doing it remotely. Unfortunately, circumstances didn't allow me to be there. I'm going to be presenting Cashew, ML input data processing as a service, and this is work that we've done in the systems group, Professor Klimovich's group specifically, in collaboration with some folks at Google. So before I begin actually presenting our work, I think it's important to show kind of how ML workloads are traditionally structured. You have your data stored in some storage layer such as S3. And then you fetch this data, and as part of your input pipeline, you apply some transformations on it, and you produce some batches. This whole process runs on CPUs. These batches are then given to the model that trains on top of an accelerator, such as a GPU or a TPU. Now, in this work, we're focusing specifically on the input pipeline and improving its performance. The logic of the input pipeline can be very diverse, and it's very much context dependent. A simple example from image classification is you decode some images, apply random transformations on them, and repeat this process until you produce batches, and then you give these to the model. Now, the problem with this monolithic design, where you do pre-processing and training on the same machine, is that oftentimes your input pipeline falls behind in terms of performance to the model. And this is because models use very high performance specialized hardware, and input pipelines run on slow or just general purpose CPUs that aren't able to keep up with the model training. And because both of these things are on the same machine, you can't really scale out the resources for your input pipeline in order to alleviate this bottleneck that is caused by preprocessing. So this ultimately costs you a lot of time, slowing down your training process, and a lot of money because you're leasing expensive accelerators instead of using them, and they're just idling instead of being used for training. To give you some concrete examples, here we have 3 models, ResNet 50, EfficientNet V2, and RetinaNet. And we're plotting the epoch times of these models as we're adding more CPUs for preprocessing. And we can see that as the preprocessing resources increase, the epoch times go down. So when your input pipeline is a bottleneck, you need to fix that to reduce the training time. Now, moving beyond this, studies from industry have shown that a small set of unique input pipelines account for most of their computation in their data centers. This is something that comes from Google. For them, 10% of these unique input pipelines account for 72% of the computation that they dedicate to preprocessing. And in Meta, they've shown that they actually use up more power for preprocessing than for training oftentimes. So this brings up some opportunities. You could use scaling out, giving more resources to preprocessing in order to avoid this input bottleneck. And you can use caching to materialize the transformations of your input pipeline, avoid redundant recomputation, freeing up resources for other jobs, and reducing power consumption. Now, the current landscape in ML preprocessing doesn't lack the fundamental mechanisms for doing this stuff. There are already solutions for disaggregating the input pipeline from the model. And by disaggregation, I mean that preprocessing now takes place in a set of nodes that is disjoint from the set of nodes that are doing the training. A framework that does this is TF Data Service from Google, for instance. This is open source and is quite well known. The real challenge comes in actually generating some policies that are able to allocate the right amount of resources for preprocessing. As a practitioner, you could try out a lot of different combinations, but this is very time consuming and does not scale. And as soon as something changes in your input pipeline or your model, you have to redo this entire process. So manually finding this number is very challenging. And similarly, caching already exists in terms of the fundamental functionality. So there are operations that allow you to materialize your data to disk. The real question here is when and where does caching make sense in your input pipeline? Because sometimes as part of your preprocessing, you increase the size of your data. And then when you read back from disk, it actually might be more expensive to do that than just recomputing it from scratch. So automating these two things is essential to improve the performance of preprocessing and ML workloads. So this brings us to our main contributions in this work. Via our autoscaling policy, we address the question of how many resources should be assigned to preprocessing. And via our auto-caching policy, we address when and where should the data be cached in the input pipeline. Okay, so let's take a look at the architecture of our system Cashew. And before I begin, I want to point out that we're building on top of TF Data. And this is because, as I mentioned, this disaggregation mechanism is already present there, so we don't have to re-implement it. It's a well-known open source system. It's meant for large-scale distributed ML workloads, and it's impactful for both industry and for research labs in academia. As part of this architecture, we have a set of entities known as the clients. These possess accelerators, and now they are exclusively tasked with training and no longer with preprocessing. As part of Cashew, we have then another set of entities called the workers. These are equipped with just CPU and memory. And these are stateless entities that just fetch data, preprocess it, produce batches, they give it then to the clients. Liaising these two entities is the dispatcher. This is essentially an entity that also implements the logic of the auto-caching and auto-scaling policies. We also have a caching layer where we materialize data. And then outside of our architecture is the source layer, which can be object storage generally, where the original data lies. So how does the interaction work? Well, a client contacts the service, requests that its input pipeline be preprocessed in the service. The dispatcher recruits a worker, and the worker will start to read the data and generate batches for the client. It will get the data from cache if it's there, otherwise from the source layer where it was initially intended to be. And in this toy example, we assume that the client is input bound still with one worker. So the dispatcher decides to add another worker. To fix this input bottleneck, the worker starts to read data from wherever it can, and then it produces batches to the client. And at this point, we hope the idea is that the client is no longer input bottlenecked. And because this is a long-running service, different clients come in and they benefit from the auto-scaling and auto-caching policies of Cashew. So the main selling points of Cashew are the multi-tenancy support, the disaggregation, the auto-scaling mechanism, and then the auto-caching mechanism that allows both cross-jobs. So one client caches the data, another client is able to read that cache data as well. And inter-job cache reuse. So you basically just cache for yourself the data, and then you avoid recomputing batches over and over again. So because of time constraints, I'm only going to focus on the auto-scaling policy, but full details for the auto-caching policy in the paper. And to understand how the auto-scaling policy works, we need to understand how a batch is being processed in a client. So before the forward and backward pass can be done on a batch, the client actually needs to get that batch from somewhere. Clients are equipped with a local buffer that is populated passively by Cashew with fresh batches that it pre-computes. Now, if this buffer is populated, then the client basically never needs to wait for data. Otherwise, if it's not populated, it will need to wait for a new batch to be produced by Cashew. The other part of the batch processing is the actual forward and backward pass. And for every single trainer node, this is expected to be more or less constant because we don't change the number of accelerators per training node during the actual training process. Together, these two make up. Okay, well, together these two make up the batch processing time. And the intuition here is that you can keep adding workers to reduce the fetching time, but you cannot reduce the actual training time. So to give you an example of how this works, imagine that initially this is your batch processing time. You add workers, you notice that your batch processing time is getting reduced, and this is because your fetching time is getting reduced. Eventually, you reach a point where you eliminated the fetching time, and you're only dominated by the model training time. At this point, you've added an extra worker that is superfluous, you remove it, and you converge to this number of workers where you have initially eliminated the fetching time. Now, there's not much time left, I think, about a minute, so I'm just going to rush through this to this evaluation. Essentially, we're looking at the ResNet 50 model with its input pipeline, the ImageNet dataset, and we're kind of studying how the auto-scaling policy works in 3 different modes: compute, point where we're caching after the source and at the end of the input pipeline. And we're comparing this with the Kubernetes horizontal pod autoscaler decision. So here we have the epoch times as a function of the number of workers assigned to preprocessing. And the idea is we want to see that our policy finds the right scale that is not over or under provisioning preprocessing. And this is exactly what Cashew does. And this is not what Kubernetes does. In a nutshell, Kubernetes' hardware signals are not sufficient for these sort of workloads from the ML domain. So in conclusion, data preprocessing is essential for ML workloads. It's a bottleneck that causes very expensive accelerator stalls. To this extent, we propose caching and pipeline as a service system with the auto-caching, auto-scaling policies, multi-tenancy support. This is all open source, and just generally, this is a very rich topic for future research. Okay, thank you very much. And if there's any questions.
Okay, so thanks for this talk. Do we have questions to Dan? Yeah, Tom?
Thank you. Excellent talk. I have a question about this policy of basically caching. So are you changing the order of what you would bequest from the dataset in any way? As a follow-up question, would you change the accuracy because you were doing a certain caching or you were fetching certain augmented or pre-processed images?
So I think these are 2 questions in a sense. If we're changing the order and if we're affecting the accuracy because we're materializing random transformations. I assume you're referring to that. So certainly, in terms of the order, we've not studied this. By caching, you will affect, in a sense, the order, but this is not necessarily bad because generally you do want to shuffle your data in your input pipeline. This is something that is done quite often, especially when your data set is relatively small. And this is essentially will introduce a window shuffle by caching your data and then reading it. There's no ordering guarantees that we give. But in our experiments, it didn't affect accuracy, at least in any significant way. Now, in terms of materializing random transformations, that's true. So the random transformations are there for a reason, and you don't want to just trivially materialize everything because that affects the robustness of the model. But there are more intelligent ways of caching. We rely, in a sense, on the user to hint for us good locations where they see caching as a good solution. And we expect them to still leave a bit of randomness that takes place after the caching operation, such that the data diversity is not really affected, but you're still getting a lot in terms of your input pipeline throughput. And there are studies on this as well. So data echoing, it's a study that explores trivially repeating preprocessed data quite a lot, and they seem to get quite decent results. So in spite of just trivially reusing data, and then there's also more advanced ways of caching and then reusing data by leaving just the lightweight random transformations, image flipping, for instance, and all sorts of these relatively lightweight operations just after caching. I think there's a paper called Revamper that looks at this stuff. So definitely you have to be a bit careful about this, and we'll choose the best option in terms of throughput, but there are ways to cache random transformations and still get a good accuracy on the model.
Thank you.
Okay, so I would suggest we keep to schedule and thank Dan for his great talk. And as you can see already, we have Foteini in the line. She is a PhD student, also at ETH Zurich. She's in the lab of Anna Klimovic. And yeah, please, Anna, please, Foteini, start with your talk.
Can you see my screen? Can you see my screen?
Yes.
Okay, so I'm hearing okay, right? Okay, yes, you can hear me. So hi, everyone. My name is Foteini. Unfortunately, due to COVID, I couldn't be with you today, so I hope you just enjoy this virtual presentation. Yes, I'm a first-year PhD student at ESL Group, and I'm working closely with Professor Anna Klimovic. And this is our current work, our ongoing work about efficient elastic training over transient resources. So we all know that machine learning training is very expensive, and the reason why this is so expensive is because it consists of multiple compute-intensive operations that need to be executed on top of high-end and expensive accelerators such as GPUs and TPUs. And it is also known that training is an iterative procedure, and it takes a long to converge to a good enough result, even if we have clusters with hundreds or thousands of machines. And just to give you a bit of an example and a bit of an overview, training a language model such as GPT-3 takes around $4.6 million, while training a model such as AlphaGo Zero is estimated to cost around $30 million. And as models and datasets become larger and larger, their cost to train will become even higher. So in this plot, you can see the number of parameters of proposed models over a past couple of years. And you see that we were at 2018, we were around hundreds of millions of parameters, and now 2022, we're around hundreds of billions of parameters. That means that the models are becoming larger, they require more resources in order to get trained, and that will mean that the cost will continue to increase. So a very interesting way to reduce cost, especially in the cloud, is use transient or spot virtual machines, which are offered by all the providers essentially, so AWS, Google Cloud, Azure, at much cheaper price compared to the on-demand VMs. And they are like around 60 to 90% cheaper than the regular on-demand VMs. And here, for example, you can see a case where we have GPUs and TPUs and their current prices in Google Cloud. And you can see the on-demand price and the spot price. And it is quite obvious that we can get these V100 or A100 GPUs or TPUs at a much lower cost compared to getting them on demand. So this can lead to huge cost savings. However, this has an important caveat. And it's that these resources are basically preemptible. That means that the provider can get them away from the users at any point in time. There are no guarantees that the user will continue having these resources throughout the lifetime of the training workload. And the availability of these resources essentially depends on the cluster demand and also the policy of each provider. So what we did was to characterize the availability and the behavior of these transient accelerators in Google Cloud over a time span. And in these figures, you can see the availability of TPU cores and A100 GPUs in Google Cloud for specific times of day. And in both experiments, we request a maximum number of accelerators. For example, here we request 128 CPU cores, and here we request around 64 GPUs. But we plot the current number of accelerators in our cluster, which is basically how many accelerators the provider can give us at any point in time. And you can see, first of all, that preemptions can be quite bulky. That means that here we lose a significant portion of our resources in a very short amount of time. And also you can see that the resource availability highly varies over time. So there are some points in the day where we have a low resource availability and some other points when we have high resource availability. And overall, the preemptions are quite unpredictable. And that leads to having dynamic environments, which we cannot exactly predict their behavior. But as we saw, using these VMs, using these nodes can lead to important cost savings. So it would be very beneficial to be able to use them efficiently. So the next question that we ask ourselves is how good are current machine learning frameworks in training machine learning models in these environments, in these dynamic environments. And we can partition the current machine learning frameworks into two categories based on how they treat the available resources. Can be either static or elastic. So static machine learning frameworks are basically the default case, for example, default PyTorch, default TensorFlow, that assume that throughout the lifetime of a training job, the resources will be always available. That means that if a resource gets preempted, all the other resources need to wait until this node joins the cluster again. So we evaluated native PyTorch, which is like the static resource allocation, in two scenarios. One is when we have low preemption rate and high availability, and the other is with high preemption rate and low availability. And we compare to running on demand, which means we use on-demand VMs without preemptions. And in this figure, we plot the on-demand case and the preemptible case, and we plot the time to reach target accuracy with a simple ResNet model. And we see that in the case of high preemption rate and low availability, we are up to 2.2 times slower than on demand. And the main reason for this is, as you can imagine, is because these static frameworks have to stop when a preemption is happening and have to wait until all resources become available. And also, even when all these resources are back and ready to be used, they experience long reconfiguration times. For example, for a cloud VM equipped with GPUs to be able to start running and can continue training, it requires around 6 minutes to get everything done and up and running. That means that the rest resources that are supposed to be active remain idle during this time, which translates into a huge waste of cost and energy. So this approach is not useful in this case. Now, regarding elastic frameworks, we again can partition them into two categories: the ones that consider a variable global batch size through execution, and the ones with a constant global batch size. So the first category scales the global batch size according to the number of the available resources. So let's say if you have more GPUs, then you have a larger batch size. If you have less GPUs, then you have a smaller batch size. But then in this case, as you can imagine, the user needs to decide what to do with the rest hyperparameters, such as the learning rate. This, of course, requires some expertise that not all users have, and is quite model and task specific. So this is why these approaches are not so much used in practice. And recently, a couple of approaches have identified this issue and trying to maintain the same global batch size regardless of the underlying resources. But we have evaluated these works in practice, and we have seen that they are quite suboptimal. So they spend too much time in reconfiguration. So whenever a change in the cluster happens, that makes them non-ideal for the case where we have a large number of reconfiguration, a very highly dynamic environment. And also they partition the workload in the number of available resources, taking into account, for example, only the memory footprint of the workload, which causes a large hardware underutilization and inefficiency. And in order to be able to train over this elastic environment in an efficient way, we're trying to build a system called Sailor. And this is an overview of our current system. So Sailor consists of two types of nodes, the worker and the controller. The workers are normal PyTorch or TensorFlow nodes that operate on a pool of accelerators, while the controller is responsible for the whole training orchestration, detecting failures, reconfiguring the cluster, and partitioning the workload into the available workers. And
2 minutes.
Yeah, just some key features. So we're trying to aim for seamless reconfiguration, not stop the training at all. So that's why we reduce the reconfiguration time to a couple of seconds compared to a couple of minutes in other frameworks. We want to leave the global and local batch size intact so that the user don't have to think twice when they use our system. And we make sure that whatever is happening underneath, like whatever is the number of available resources, we ensure that the data sample is seen exactly once throughout an epoch as it should. And our system currently supports only data parallel training, but of course it's our current work to enable pipeline parallel training and enable larger models. So we compared our system with Varuna, which is also another elastic system training on preemptible resources, and also with native PyTorch running on demand without preemptions. And we see that we're quite faster than Varuna. We're 1.3 times faster than the other elastic system. And also we're much cheaper than the on-demand case. We're 2.8 times cheaper than the on-demand. And as an ongoing work, we're trying basically to make this line here, this Sailor line here, much smaller and reduce the training time. And the reason why we are a bit slower than the on-demand is, of course, as you can guess, as we train with less resources, we need to serialize a part of the parallel computation. And what we're trying to do now is to see if there is a way to share compute or memory across different layers or across different paths of the network in order to minimize execution time and utilize hardware as efficiently as we can. So this was a very brief overview. Thank you very much. And if you have any questions, reach out.
So do we have questions for Teni? So maybe I go ahead. If you show these benchmarks where you essentially show how the time varies to reach a given accuracy of your algorithm, right? So in these benchmarks, did you actually check how much what you define as accuracy, essentially the limit
Yes.
where you say, okay, now we reach accuracy, has an impact on these essentially relative scalings, right? So
Yes,
is that always
exactly.
constant for all measures of accuracy, or does that actually vary and depend on that?
Yeah, so this is a good question. This, of course, varies according to the target accuracy. And another thing that affects this time is also the availability of the machines. As you can imagine, if you have a very an environment with with many preemptions and very low availability, these lines that utilize preemptible resources will go up. And if you have an environment with high availability, these lines will go down. So it depends on the end accuracy and also depend on the target and also on the environment. So there are two main factors that affect this execution time.
Okay, thanks. Are there any questions from the audience? Okay, so I guess in that case, we thank Foteini again for the great talk. And then we continue with a panel discussion. So I would like to welcome the panelists to the front. So, Tal, Luca, regarding the microphone, we probably
have two microphones. I think
one for the questions and then one shared around amongst you. Okay, so I'm actually happy to have a panel discussion now after having heard so many different talks. Let me just briefly try to explain to you how this is going to go. So I'm actually going to try to start the discussion among the panelists. You already know them. We have Tal, who is a senior scientist and lecturer at ETH. We have Luca, who is leading the digital circuits group and systems at ETH Zurich, and also a full professor at the University di Bologna. And of course, we have Marina, who's actually co-organizing this event. And Marina jumped in quite spontaneously since Bill McCall jumped off. So thank you very much for the quick change of plans.
It's a pleasure to be here.
The idea is also to make this very interactive. So I'm actually going to kick it off, and then I will essentially forward the word to questions from the audience. So please feel free to then also bring questions into the discussion. Okay, so maybe to start, I can already tell you I'm the alien here. So I'm not working on high performance computing. So maybe I try to explain you what kind of a day-to-day life in my group looks like, right? So in my group, we work more kind of on applications of high-dimensional statistics and machine learning to the world of genomics and personalized medicine and cancer, right? And often what we spend our time on is actually an equation where we already know the exact solution, and we try to find an approximate solution, because essentially, even though we have the exact solution, we cannot run it just because the computational cost is too high, right? So my question is to you, and it's quite a provocative question, obviously. How long will we need to keep doing that? How long will we need to keep finding MCMC approximations to solutions that are already given?
It's a tough question. I think that for some time now, you're going to keep doing that, right? But with very recent developments like Alpha Tensor, I don't know if any of you have read this paper. So basically, DeepMind were able to make an algorithm into a game. And the algorithm was matrix multiplication on a certain tile. And they were able to reduce the number of operations necessary to compute that matrix multiplication. So basically reproducing algorithms like Strassman's algorithm and even others. So maybe in the near future, researchers will formulate their problems as games and run a reinforcement learning on it. Who knows? Yes, I think so.
Maybe, let's say, more and more, I think the mindset, I think there were a couple of talks that also the NVIDIA talk, the mindset of scientists is changing a little bit. The boundaries are blurring a bit. So in the past, there was like some rigid boundary, like double precision floating point. Because on one hand, the scientists would like to have the peace of mind that the calculation was numerically correct, stable, and so on and so forth. And this was like some sort of a wall that people did not cross. Now people are really starting to realize, out of desperation, nothing else, because there is really no way to even in the future, with the slowing down of technology, to solve the problems with order of magnitude more hardware, because the hardware is not really improving that much. So people are now more willing to negotiate. And so one direction will be really more and more algorithmic co-design, where you don't take the equation, you assume infinite precision. If not infinite precision, the next step, which would be double precision floating point, and then you ask your computer to solve it. But you will, be more and more vertical, try to find the solutions. So I think that the future will be that there will be more and more co-design, not because people are like to do it, it's out of desperation, but that I think will happen.
Yeah, so following up on this, so that I don't think any of us have given an exact timeline, and it's hard to say that, but as we've heard in lattice gauge theories, we are also using Markov chain Monte Carlo in order to solve this large sparse system of equations. And well, if we would have an infinite compute time, then we wouldn't need to resort to all of the optimizations that we are discussing now. But I think we are far away, at least for this particular application. Again, it depends from use case to use case, but for lattice QCD, we are far away from having so much compute power in order for all of this work not to be necessary. So I think, I don't know, at least for a decade, I would say, but probably longer, we would need to.
But do you think it's going to happen eventually?
Well, it's in conflict with Moore's law, so I'm not sure it's going to happen eventually. I mean, I think somebody did a calculation, what would be the size of high-performance computer with current technologies in order to perform a computation that we would like to have in order to understand all the fundamental physics, and it's pretty big, doesn't fit so neatly on Earth. So I think we would need to do that in a while now, unless some breakthrough in technology design happens, which would minimize the size of the high performance computing.
Okay, I see. Yeah, I think that's already getting interesting. So now we're kind of going into the areas of specific applications, right? And obviously people here have different backgrounds. So can you think, so obviously we can, for example, kind of have a broad dissection already into simulations that we can perform, which is probably more the area that you're working on. And then we have the side of learning algorithms that essentially learn from data. So do you see areas or applications where you think, or even scientific breakthroughs that could be solved by that, where you think advances in high performance computing could be particularly useful compared to other domains?
I'm not sure I understood the relation with the learning that you're trying to make here.
So there doesn't need to be a connection to the learning. I was just saying that, so we have roughly, we can kind of dichotomize into two sections. So one, we have simulations that can be done, that is more often done in physics, obviously not mainly, but then we also have the world of machine learning and statistics, where essentially we learn from data. So these are, they don't need to be that separated, but obviously they are in nature two different things.
All right. Yeah, I think I get it now. Yeah. And I won't talk much about it, but we will have a few talks over the next few days going in this direction, explaining how or giving some test examples where Markov chain Monte Carlo simulations could be made more efficient by using machine learning, for example, in order to generate Monte Carlo samples, for example. And this is one of the bottlenecks in lattice QCD computations. Not anymore the only one, but so one very expensive thing is solving the Dirac equation, and this is what Kate discussed earlier today. But another one which wasn't discussed at length is critical slowing down, which we get when we move from the unphysical simulation in a computer to the actual physics that we are trying to understand. The cost rises exponentially, and one of the proposals to solve this problem is to use machine learning in order to speed up or to change this rising cost when we approach the physical point. And we will have a talk by Dennis Boyda, who was connected also today, and Andreas Schindler, and a few more on machine learning as well over the next few days. So there is an attempt in our community to merge the two.
Wanted to add that what you're basically referring to is data-driven modeling. I mean, before the age of deep learning, we did these things, right? So in terms of numerical weather prediction, which is, of course, kind of my home application here, you know, all the way back to the 1980s, people were trying to derive from data certain parameterizations of certain subproblems. And these days, with, you know, the abundance of data and the computational power and the level of machine learning that we can actually do, I think it's more of a problem of really kind of choosing, like selecting your sub problem that you want to solve, right? Like you need to select wisely. I wouldn't use a machine learning model to learn end-to-end weather prediction, but I would use it to learn parts of that pipeline that I would consider to be learnable in terms of, you know, kind of data-driven modeling again. Yeah.
So you're essentially saying any problem that can be split up into these small chunks.
I guess I don't know the size of the chunks, but learnable chunks, parameterizable chunks. Yeah.
Okay. Yeah. And then we have a question from the audience. Could someone please pass the mic?
Yeah, so sorry, you saying that made me wonder, is these chunks actually about being able to make sense of what's coming out of the model so that you have a reasonable expectation of what it is your model's learned? For instance, in simulation, we have several chunks that simulate different parts of our detector, and we have a very tight idea as to what we expect out of that chunk, as opposed to just simulating the whole detector, at which point we would be a bit lost if it wasn't working well.
Yeah, so I think that's an excellent point. I think that's also kind of related to another thing, you know, so the chunk is not necessarily spatial. I would say it's more kind of the depth of the computational depth, right? If you're simulating a small part of a detector and you're trying to learn that, but you know there are so many things that would affect the output or the outcome, then your models won't be, you know, representational power, or they wouldn't be able to represent this nicely, or given data that they wouldn't anticipate, you might not get the answer that you're expecting, right? So that's another thing to consider, right? It's also that.
Okay, thanks for the question from the audience. Do we have another question from the audience? Not so far.
Yes.
Ah, great.
Hey, yeah, so this is, I guess, also relating to this whole workshop. You mentioned the example earlier where I think you mentioned a bachelor student looking at some code of someone else and then they optimized it to a high degree. How do you make sure that, I guess now everything's becoming much more specialized, and I mean, you're an expert on data management, and how do you kind of make sure that people still talk to each other to the degree that where you can say, someone can come to you and be like, hey, we have this, can you optimize this for us? Or in the case of someone else who might have, I want to optimize this, how do you make sure that you're available and talking to each other, which I guess this workshop is all about. But
yeah, so this question is, I assume, right? So yeah, I can talk from personal experience, right? I've been a performance engineer as a trade, as a profession, you know, for several years, and then also doing my PhD when I was doing computational chemistry. And in that sense, I found it always troubling personally that I would have to go to the physicist or the chemist or whoever's application that I would have to optimize. I'd have to go to them and spend over a month just understanding the program itself. Even though in the end, the optimizations that I would do were, you know, quite independent of that. They were always about data movement, right? Hence this entire approach. And that to me, like, okay, talking is important. I can give a counterexample to what I'm saying right now. But to a certain degree, performance engineering can be done completely without any knowledge of the domain on its own, right? I would say that with Lattice QCD, for example, the Tensor Core optimizations that were being done, right? So one of the keynotes, right? So this is one of those optimizations where I know, okay, I lower the precision. I have to do it in a smart way. I have to regain that either through more iterations or something like that. I think, yes, those things can be done. And then to counter my own point, some optimizations, like algorithmic optimizations, I don't think that you will be able to maintain the separation of concerns when you have to change the algorithm. You have to understand, you have to speak to the person who is actually, designing the problem. And yeah, I mean, there are limits to each one, and you can probably model with your current algorithm, like where your kind of peak is or where your upper bound is. And that's very helpful, right? It might not fulfill your constraints. Hope that answers it.
Maybe one added point on this is I think it's also very, establishing some sort of a common abstraction is very important, because many problems that are fundamentally hard to solve in the decoupled way, they can become much more suitable to a reasonably efficient computational solution if you open up a bit the boundaries. And one of the key points is that people that are mostly focused on the model, on the mathematics of the or on the physics model, completely ignore what are the computational implications of this physics model. And this, I think, requires a lot of work of people that have to undo this and go back and understand. And sometimes it doesn't mean that you have to compromise accuracy and so on. It's probably there are dual formulations. There are a lot of mathematical tricks that can, without giving up the ultimate accuracy or asymptotic properties and so on, that can actually improve a lot the solution, the computational solution of the problem. And what happens is that people, there is really an effort to have this common language. And even more when you go to the hardware, which is where I live, there is another second jump. But it would be nice also just to have only one of these two jumps done.
I agree very much with what was said earlier by Tal and Luca, and that's a very good point, Mika. I would also like to add that many universities or computing centers are investing in having the team of dedicated performance engineers who would help physicists make their applications more scalable or more efficient. But yeah, in my experience, it really takes a while. Maybe we don't know the language yet, but it usually takes I don't know, a couple of months to get the common dictionary going, and then after that everything is quite easy in a sense. So I think it's worth investing in that. I don't know what's the best way to organize such investments, but I think it's worth investing in some joint dictionary where then it would be easier for you. But I also wanted to ask the panelists, is this future computing lab meant to do something like that? You indicated in your talk you would like to have Python code that you might test and so on. So is it meant to be as a hub for helping us at ETH optimize our code?
Definitely. So I was going to, if you weren't going to say this, I was going to say that's exactly why we're touching Python or high-level languages, because there you actually specify your problems in a more algorithmic, high-level sense that you can play with. Not to have to undo. And this undoing that you mentioned was exactly something that we were doing a lot. Like a lot of things, like for example, are just not cache friendly, and so just have to go and break them down into the components. So yes, so having a high-level language, yeah, I think that's the common language.
Maybe to elaborate a bit on these high-level languages, one of the issues that we had in the past as, let's say, hardware software engineers more than algorithmic, working the algorithmic level with these higher level languages is that they tend to become narrow, in the sense that you tend to have domain specificity in these languages, and sometimes the domain becomes so narrow that there is not a large enough community to support all the software engineering that comes with a very narrow language. This situation somehow, is improving because there are now also the software engineering field is maturing with this respect and so on. And I think that one of the big examples of very strong domain-specific environment, which is all the stuff related to machine learning, is emerging and really helps this vertical optimization. And one of the big problems is that many of the legacy high-performance computing software packages and so on were developed in an era that was before that. So you have general-purpose languages like Fortran and C and so on, maybe wrapped into libraries, as you were explaining, that are somehow blocking the situation. If we could undo some of these at the community level and have some higher level specifications, maybe in domain-specific languages, but then the domain-specific language can leverage a lot of the algorithmic machinery that is being developed across many independent, let's say, more agnostic optimization flows and so on. So I think this is happening. And again, the reason why it is happening is not that people like to do things smart, is people are desperate because they don't get enough performance. So they have to go through this.
Okay, yeah, I think that we are already heading in a very interesting direction. So essentially, when we talk about the speed up in terms of time, so time is essentially determined by both hardware, software, and then, as you said earlier already, the essentially mathematical complexity of the problem, right? So essentially, as you said it, as you made it clear, kind of the connection between the software and maybe, let's say, the mathematical problem itself is really finding one common language that is spoken in terms of programming language. How do you think the connections could be further made between the hardware side and the software side? Is there a strong connection? Are people collaborating a lot, or are these rather kind of distinct research groups?
Okay, no, I think things that we are doing, for example, in the Future Computing Lab, are really to create this sort of groups of people that look at the problem at the different viewpoints and come up with creative solutions that could not be done by only one of them, the hardware guy or the software guy or algorithmic guy. But there is one point I want to make that, in my view, is the next revolution we have to do in terms of how we think of these computational problems. So the first revolution was to move from, let's say, sequential to parallel. And this is right now, I would say, most of the people acknowledge that even the normal programmers can use GPUs and so on. So this is done. The next one we have to look is, at least in the transition between algorithm and software specification, is data movement, as you were saying in your talk. So I think that most of the people right now, when they think, just to give you an example, most of the people, when they think about optimizing an algorithm, they think about reducing a number of elementary multiplication and sums. Okay, yeah. Even the paper that you were citing before was in a sense reducing the problem to let's do matrix multiplication with less products. But this is not the right way to look at it from a hardware viewpoint, at least from my viewpoint as well, because most of the work you have to do in implementing in hardware and algorithm is moving stuff around. And most of the power goes there, most of the performance goes there, and so on. So there are many examples, and we discussed many of them with Thorsten and so on, where doing more computation, more multiply accumulates, would improve the performance of the algorithm because you have to move less the data. Okay, yeah. So some computational replication actually will help improving the performance, overall performance. And this, I think, people still don't understand, because people are, think that what you have to reduce is the number of calculations, but really what you have to reduce is the data motion. So this requires a further Copernican revolution to handle, but it's going to come.
That's a really good point. I would like to go back in the history to this to give an example of this connection between hardware and software. So, for example, a little bit over 20 years ago now, the lattice QCD machines were designed specifically so that the community, together with hardware engineers, would design the chip such that the computation could be done in the most effective way. So now, in the meantime, this approach has been abandoned since the industry standards have changed, and it's much more cost efficient, at least, to buy or run on a dedicated high performance computing hardware. But all these developments also in the industry of supercomputing was followed by dedicated tests of our software the software from our community on these new machines. So I think this synergy was crucial both for the fields to progress, but also for the hardware industry. So I'm looking forward to seeing what can be done also in the future in this direction. And for the younger part of the audience, you can look it up. These machines were called APE, and APE Mille, yes, this is one of them, but there were several. APE 100, I think, was also there beforehand, and so on. And this was an exciting time, and it would be interesting to see whether something like that might be useful also in the future. For the last decade, we definitely knew that this was not the case, but if you, as you mentioned, so Luca mentioned in his talk that the cost of designing dedicated chips is going down, so it might be an interesting thing to look into in the future as well. But I had a question regarding the data movements that Luca just mentioned. So, so you're saying it's more efficient not to to even have more computations than one currently has, as long as one has less data movement. Is it also more energy efficient?
Yes, and the reason is quite obvious, and I think as a physicist you will understand it immediately. Is that you cannot play with the speed of light, right? So there is you can play with many things, but not with the speed of light. And so if you have to bring something from far away, this is going to take a bounded amount of time given by the speed of light. And energy is the product of time multiplied by power. So, you know, if you have to bring something from far away, T is going to be large. And yeah, you can try to make P small, but one of the two parts of the equation is very large. And there is no way around it. While, you know, if you, instead of moving things around, you repeat the computation, then it's local. The T, the speed of light effect becomes smaller because you don't have to move things from far away. And then you can, you know, you can make this contribution smaller and smaller by the fact that it remains local. So if you improve your devices to some degree, you can, you know, still get improvements. And we see more and more this effect, where recomputing is better than bringing things or moving things around. Just to give you an example, when you tile a large tensor, there are, especially when you do convolutions, there are overlaps between the tiles. Now, the obvious thing to do is, no, let's not recompute. Let's just send the partial results of the boundaries between the tiles so that everybody gets it. And this is what people tend to do in this systolic type of computation. It doesn't, if you think about it, this distance is very small. So it means if the pattern of communication is very near neighbor, then it makes sense. But if you have an all-to-all communication, then it's totally meaningless to do this, because the cost of pushing the partial results around will blow up completely the cost of recomputing them. So in a sense, people needed to start thinking about this, because it's fundamental and it's not going to change in the future.
I would like to give an example from deep learning. So related to also this DACE-ML project, one of the things that we did there was to do recomputation on a global scale, because when you are, you know, doing backpropagation for training, so like auto differentiation for training, one way to do it is using backpropagation. And so you might store your partial results, obviously, to in order to recompute the gradients. We found that in many cases, the knobs that you can tune between recomputation and just reading this data a lot of the time you would go for recomputation, and that gives immense performance benefits. So first of all, you saved, like for one example, like an activation function might be 100 megabytes that you just are not moving anymore. You replicate exponent, log, I think, and other, I think 2 other multiplication operations. It's still worth it. It's going to be something like 3 times faster or something like that. So really, there is no, like, you really should think more about recomputation. And I'm sure there are cases in, you know, other scientific computing applications where we need to rethink about recomputation. But I guess the abstractions are not, it's not easy enough for us to see when we could actually recompute something. I think that's something we need to change in the programming model, and maybe the representation, maybe we could see if we could do this. And yeah.
Okay, so I think that was a lot that we digested here. So maybe we can try to find one final topic before we essentially conclude the panel discussion. And as a warning, it's a bit more political, but maybe we can try to approach it from a more scientific perspective. Maybe also we try to keep it short because I think time is already pressing. So you know, high performance computing has always been about pushing boundaries, but now we're essentially running power hungry computing resources in places where energy is generated by fossil fuels will become increasingly hard to justify, especially now that essentially the financial and economical or environmental costs are increasing exponential.
I can say one thing maybe very quickly. So green AI is kind of a phenomenon now, and this is happening and being pushed actively by researchers and industry alike. Maybe the other thing is that, you know, cruise ships also take an immense amount of power, more than supercomputers, some supercomputers maybe, yeah. So yeah, that was my point.
All right. Well, that's a very important point, and thank you, Fritz, for asking that. Yeah, so I will give a few bright examples, at least from our experiences with dealing with high-performance computing centers. So we run a good part of our simulations on CSCS in Lugano, and something that I loved very much when I moved back to Switzerland. So I used the machine also upon my previous stint in Switzerland when I was at CERN, maybe 7 or 8 years ago. And in the meantime, I've seen that many changes, for example, into the application process. With each job, we get an energy report as well. So when we are applying for computing resources, we also need to justify. So it's not only the sweet spot for strong and big scaling, but also energy scaling is something that plays a role when we make a plan. How are we going to run our resources? So I think raising awareness is an important thing, and we are moving in a good direction.
I take my last comment on the hardware side. So I have to say that there is also an extremely fun and interesting area of research, which is like we have to learn how to design more fuel efficient cars. We also needed to learn how to design more energy efficient computing systems, not only the processors, the memories and so on, but also the cooling, the energy recycling and so on and so forth. So there are very interesting technologies that make the so-called PUE of a compute equipment 0.02, which basically means only 2% more of of your budget that goes into the computation goes into the cooling and infrastructure and so on. That like liquid cooling, multi-phase cooling, and things like that. So I think this is a very serious concern, and we should take it seriously from the application viewpoint, also from the awareness of the user viewpoint, but also from the technology viewpoint.
Okay, so thank you very much for your comments. So I would say we thank the panelists again for their contributions here. And then I guess this discussion can obviously be continued at the apéro in a second, but before we do that, Marina is going to give some concluding remarks.
Well, thanks everyone.
Thanks.
Thank you. Roman, I'm sorry, your computer is locked. So first of all, thanks everyone for showing up today, both in person and our colleagues who couldn't be here in person, but who connected via Zoom. We've enjoyed very much our keynote, and thank our keynote speakers, then our student talks, and thanks also to the industry colleagues who joined with their stands and with their talks. As you've seen, this is an important and emerging issue where as we could collaborate even more between different fields, and I hope that in the next days of the workshop, so also this evening and in the next days of the workshop, we will be able to start at least these collaborations. So I have uploaded instructions how to get to the Apero. Let me just download them and show it to you here. So the Apero is not going to be in this building. It is going to be in the Bella Vista restaurant, which is, if you get out, we are now in HIT building. If you turn left when you get out, and then on the right, you will see the list. So this is unfortunately my inability to use a Roman's computer. Can you help me, Roman? I'm just, it's, I just, if you can just go to the timetable and refresh. And you can download. I will still. All right, so it starts in about 5 minutes. That's plenty of time to get there. Google says it's 1 minute, but then it may take 2 or 3. So if you get out of the HIT building, you can see you go left and then you go right, and then you'll see this white building if it's still daytime, or this is how it looks by night. I'm not sure yet in which part. It's a big restaurant where we will be, so be patient. If you don't see anybody, try to go around and then you will see us in case you take a few minutes to get there. Otherwise, we can walk all together. So I hope you use this time to discuss what was happening today and to make some plans also for the next days of the workshop. Once again, thanks to all the speakers, and thanks to the audience for interesting questions. And we'll see you tomorrow at 9:30 again in this room. And for the Wednesday and Thursday, we will change rooms, but we'll announce that tomorrow. Oh, thanks everyone once again.